All right. Good afternoon, everyone. My name is Wolfgang Hönig. I'm an assistant professor at TU Berlin, and I'm one of the co-organizers of our wonderful workshop on area swarms, tools, and applications here at RSS. And so we get started with our program just in a few minutes. I just want to kind of introduce and motivate our work here. So our area swarms will have a lot of interest. So on the left, you see some picture generated by Microsoft Bing, what the AI thinks our area swarms are good for. And maybe we are all working somewhat into that direction of trying to have robots that can do useful things. But our area swarms are already out there. And so on the right, I listed some like concrete applications where they're used. So it includes autistic performances, like maybe the most common one is just fireworks with many drones, environmental monitoring, documentation of historical monuments, and inspection of critical infrastructure. And the exciting thing is that we actually will have people who represent all four of these areas here today, who will kind of share with us the progress they have made in the past. So the motivation for us to kind of organize this workshop is that we notice that we spend a lot of time just working on demonstrating stuff on real robots. So it takes like almost 80% of the time sometimes. And it's also difficult to even figure out what to use. So just we came together as organizers, and already within the organizers, we are developing 4 tools that kind of do the same thing. So kind of the motivation is, of course, for the users trying to figure out how do we select and also how to use the tools to make our research more efficient, specifically for area swarms, but then also for the tool developers, maybe to understand better what are others doing, what are the typical use cases, and what are alternatives. And ultimately, maybe the goal for us as developers should be to converge to fewer but better tools instead of wasting time reinventing them. And we hope we have also, like along these lines, a lot of great discussions during the question part of the presentations, but also during the coffee break. Okay, so this is not the first workshop. So there has been one workshop last year at ICRA where we had a similar theme, but we looked very specifically on simulation tools. And there was one paper that came out of these discussions. And the shocking thing is that there was like almost 40 people, 40 like different simulators that we had to compare. And that really doesn't make sense, right? So we hope that the survey paper also helps to condense maybe this insane amount. Yeah, so maybe about the organizers. So I already introduced myself. Then we have Kimberly. Maybe you can raise your hand. So both of us work on CrazyChoir 2. We have Miguel and Rafael here work on Aerostack 2, and then we have Lorenzo, Andrea, and Giuseppe, who's online, who work on CrazyChoir. And then today we have quite many great speakers coming up, and they all represent like area swarms as well. We have Gábor from Colmont, who will also present basically a tool and tutorial style, which we're very excited about. We have Sabine Hauert, Martin Saska, and SiQi from McGuire and and the schedule you already know most likely, but that's what we have on the webpage. So we start with an invited talk by Sabine, She will be remote, but we tested the audio and everything should be fine. And then everything else will be indeed in person. And we will have 4 tutorials and then 2 more talks at the end of the day, spanning area slots. Okay, and with that, Miguel can introduce our first speaker.
Hello, I would like to introduce our first speaker, Sabine, who is a professor of swarm engineering in Bristol University. He works on swarm for different applications, ranging from nano robots for cancer treatment up to larger robots for environmental and monitoring and logistics. And she has a lot of different projects, and she has raised over more than 30 million pounds in grant funding. So we are pleased to have her today to listen to her talk.
Thank you so much. Would it be okay to stop sharing the screen? It's telling me I'm not allowed to until that one's off.
Yeah, we are trying. It doesn't allow us to stop sharing our screen.
Great, and thank you. Thanks so much for the invitation. I apologize I can't be with you today in person.
Okay.
Kijk eens hier naar sturen.
Is that working?
We just have to put the Zoom meeting on the main screen. So just one moment.
Okay.
Are you sharing your slides already?
Yeah.
Yeah, I can see it. I just have to bring it up on the main
There
screen.
you go. Maybe you can close the participants.
Yeah.
Oh, many participants.
Is that okay?
Yeah, I think
Okay, great.
that's great.
Okay, thanks so much for the invitation. It's a pleasure to be here, and I wanted to focus today's talk on the work that we're doing in aerial swarming. We work in many other different types of swarming in the air, on the ground, in the water, but swarming in the air is close to my heart because that is where my journey started. And I've been fascinated by many years, as many of you here, by these flocks of birds and their ability to do these beautiful complex dances in the sky. And the fact that each one of these birds just reacts to their local environment, and that allows them to create these patterns. I also enjoy the fact that they're scalable to huge numbers and that they're robust to individual failure. And ideally, they can do more than the sum of their parts. And so this has been an intrigue for the swarm engineering community for a long time and has motivated us to put it on robotic systems. And so already 15 years ago or so, we put it on a swarm of fixed-wing robots that you saw before, about 1 meter in wingspan. And these robots had limited communication ranges, limited turn abilities or turn rates. And we applied flocking rules on them, Reynolds flocking. So they would attract to each other, they would repulse from each other, they would align with each other, and then they would go to a migration point to avoid our flock from falling away. And driving up to the farm fields, we could sit behind these 10 robots, throw them in the air, and then they would enter a holding pattern. And from that holding pattern, we would launch that flocking algorithm, and we could observe through their GPS trajectories the behavior of the individual robots. They had about 40 minutes in lifespan in terms of battery. And so we could usually do a couple flights every morning. They're also a bit bird size, so sometimes you see 2 little birds there in that video flying after them. So this is what we would see on their screen. We spent a lot of time trying to figure out how we'd look at 10 flying robots. Usually it would just be me and one of my colleagues going to the farm fields, or sometimes I would go alone back in the days when we didn't have to have backup pilots for everything. And we actually had a derogation 1 kilometer by 1 kilometer over this farm field in Switzerland to fly in autonomous fashion. And when we were ready to start our experiments, typically what we would do is we go up to our swarm command, and then we would launch our flocking algorithm. And what you're looking at here is the GPS trajectories. And so it starts very messy when they're starting to apply their forces. And over time, it converges to a circular topology, a circular dance, which is what we predicted using our simulations. Every time we put a swarm in the air, we simulate it multiple times to gain confidence in their emergent properties. Here's the circle. And we also played around with different parameters. So for example, you can make their turn rate much lower so that they can't react as much to their neighbors. So this is a low turn rate, and you can see they have trouble turning fast enough to align, but they do follow each other. So you do get these mini flocks, and we would also reduce their communication range to also prevent them from communicating with everyone, which also hinders their ability to flock in such a cohesive fashion. So this is one where they can communicate only in small neighborhoods, so you get these mini flocks emerging from those patterns. So that was taking the bioinspiration, putting it on swarms of flying robots. We also wondered how we could use these in a more applied way, and we're interested in Dario Floriano's lab at that time, and how we could use them for search and rescue, and in particular to create communication networks in disaster areas. The idea would be that you throw them in the air and they serve as relays for the wireless communication. And at that time, we were curious as to what algorithms we could come up with, because we didn't have a clear bioinspiration in that case. And so we used artificial evolution to evolve neural controllers for these robots to come up with solutions that we hadn't thought of. And in that case, these neural controllers use the compass of the robots, their ability to communicate with their neighbors, and that would impact the turn rate of the robots. We then, because they were neural networks and we weren't completely confident in the behavior of those neural networks, had to reverse engineer the behavior of those robots and then hard code the rules on the robots. And so these are some of the things we discovered through artificial evolution, such as synchronized chaining, where all the robots are turning at the same time with the same beat. And we also discovered a strategy where basically these robots, through this turning, wait for each other, grow chains, and then these chains can sweep an area. And here what you're looking at is the GPS trajectory of robots, 10 robots here linking two rescuers. They're not real rescuers, they're us on the ground, but about 1 kilometer apart, which back in the days was quite fun to achieve. So this journey on swarms of flying robots was exciting, both because it made us realize that swarming can work, I think, on these real robot platforms, and they can be quite resilient. The flocking experiment that you saw was one of the first ones that we put in the air, and it happened to work after we'd done that groundwork of making the simulations work well as well. And so the question is, how do we really bring them to the application world? And so something that's gotten us excited about is the area of forest fire monitoring and mitigation. If you look at all the forest fires around the world, and if you could prevent them, that would offset about twice the global aviation emissions around the world as well. And so a worthy goal in addition to all the economic and health impacts of these forest fires. And what's clear is most of the applications that were limited at the start, except for perhaps entertainment, require scale. They require robots to be up in the air for a long period of time, and they require them to go perhaps long distances. And ideally, in the case of forest fires, if you find a forest fire and you can even drop a payload on those forest fires, perhaps you can mitigate them or stop them from growing out of control. And so with this in mind, for the past 5 years, we've been working with a company called Wind Racers that makes a very large drone called the Ultra that has a 10-meter wingspan, can travel about 1,000 kilometers, can carry around 500 kilos in payload, or 100 kilos currently with what we're working with. And so these drones are interesting. If you're trying to cover an area the size, for example, of the state of California, or you want to do environmental monitoring, for example, in Antarctica, which they recently did. And so with this in mind, we've taken the swarm algorithms that we've been exploring in the past and really started to think about scale. What happens when you have a drone that can do this type of distance and carry this type of payload? And so we've been looking at different strategies on how you explore the world. One is a more centralized approach where you tile the world and then you do a lawnmower pattern and you dispatch your robot to each tile in that environment. And that allows you to get good area coverage of those environments. We've made it quite dynamic. So in a click of a button, you can constantly regenerate these tiles. For example, if you were to lose a robot or if you need to replan the area that you want to explore. But we've also been looking at more swarmy approaches. For example, robots that deposit virtual pheromones as a way to mark their territory, just like ants would deposit chemicals. And that allows other robots to avoid those areas that have already been explored. Or one that we've been excited about recently, which is called dynamic space partition. And that's a bit like the tiling, but done in a swarmy way. And the way we do that is each robot has a point, which is its space partition. And each space partition pushes each other away. And so all these points, space partitions, basically using forces, just like the flocking, distribute over the area to explore. And then robots go to their point and then navigate the area around their space partition. And because it's swarmy, if you remove a robot, its space partition point disappears and they can reorganize. So they can do a lot of things for free through self-organization. So that allows us to explore the areas quite efficiently at the scale of California. In fact, you would need about 30 robots using dynamic space partition to cover the state of California 24/7. And then we've also been looking at how you mitigate these forest fires. So we have a fire model where you have a small fire that's initialized, and then it grows over 10 minutes and 50 minutes. And how quickly do you need to find that fire? Again, we're looking at areas the size of the state of California so that we can extinguish them. And so with this dynamic space partition here, you can sort of see these spirals. They're the trajectories around each individual space partition of the robots. You can extinguish 100% in our simulations of the small fires, but the large fires are harder to catch. You can see here, these 5 points are little fires that are moving. So that's why you see a line, because they're moving through the environment. And so at some point we're able to stop them. But if they're medium sized, then we can no longer stop them with dynamic space partition, because a single drop of water from those aircrafts is not enough to extinguish those those medium fires. And so then we need to coordinate our robots in a more sophisticated manner to be able to, for example, one robot drops the water and then calls another robot to drop their payload so that they can have a more concerted, common effort to be able to extinguish these medium fires. The large fires, that's the point at which we need the firefighters to come in and to intervene, given the payloads that we have on these aircrafts. Or you would need to have many more of these aircrafts monitoring the environment over time. So to be able to test these systems in collaboration with this company, we've developed a pipeline which allows us to go from development of the swarm algorithms to low fidelity, very fast batch testing of the algorithms, to high fidelity simulations using their system that uses their autopilot and what they've designed to be able to run their drones. And then a system to be able to deploy them that allows us to both monitor the swarm and see what's happening in real time and control them. It also allows us to deploy virtual aircrafts in addition to the real aircrafts that are up in the air. This is what it looks like. So you sort of see the low fidelity simulation with the green background that's much faster to run. And then on the right, you see the higher fidelity simulation that uses the system that they use in real time. And our current architecture uses basically the drones that are connected to a cloud infrastructure provided by the company, and then connects to our swarm interface. And our swarm interface can either simulate drones or use real drones in low fidelity or in high fidelity, feed back the commands to the cloud control, which then goes back to the drones. So there's sort of this connection through cloud control for everything that we're doing. And then that swarm system can communicate with a swarm operator who's in charge of commanding the swarm, for example, to explore an area or drop a payload, and a safety operator for the purpose of our trials. Because unlike when I was in Switzerland and could just go to the farm fields and throw robots in the air, here you need obviously a backup pilot for everything that we're trialing in the fields. Our initial trials last year used 3 believers to test our interface and some of our algorithms. So believers are a bit bigger than the drones that you saw at the start of my presentation. They're still hand launched. And we use these because they use the same autopilot and all the same mechanisms as the larger drone as a trial. And here you see Georgios and Lucio using our swarm operator command center to be able to tell the swarms to search the area, change different actions over time. And through these trials, we've also then started to really engage with firefighters to understand what it is that the firefighters think would be a useful set of tools, a useful interface. And the first thing we realized is that there's a lot of drone operators within the firefighting field, which is very good. They operate single drones, typically remote controlled, and that they're quite open-minded. So what did we do to explore this? Well, we did two different explorations. One was to use mutual shaping. In those, we spoke with 15 firefighters, or around 18 hours of conversation from around the world. And we asked them about their current firefighting operations. We asked them, we presented the drone to them, and we asked them how they would use a single drone. And then we asked them to think a little bit outside the box in terms of how they would use a swarm within their operations. The things that they thought would be useful in terms of information was to understand more about the fire front, the environmental conditions, really be able to monitor points of interest, for example, a building or a school or a road, as well as understanding the fuel load. So where else could be burning further down the line. And then when you made them think a little bit beyond in terms of swarm operations, there's always a lot of interest in area surveillance and understanding the fire components and delivering supplies to the firefighters who might already be there. And then active firefighting became a reasonable thing, which means dropping a payload, a water payload on, or an extinguishing payload on those fires. When you start to think of a swarm with a single aircraft, that didn't come up as something that might be useful, but with the swarm, you all of a sudden get the scale to carry something that might be meaningful to extinguish your fires. We also did a contextual inquiry. And so we sent out questionnaires to firefighters. We asked them how confident they would be in using a UAV or a swarm, what their attitudes were to the drones, what their opinions were. And then we did focus groups to really hone in on what they think these systems should look like and perhaps even design a better interface. We had a lot of people from the United States, the UK, it's mostly the UK and Greece. That sort of is due to the makeup of our team. Mostly male-centric. There aren't many women in the firefighting discipline, unfortunately, but that's something that we'd love to see more of. And so a certain number of years of experience in the firefighting area. What was encouraging here is that blue gives you a sense of whether they agree with some of these statements. For example, are UAVs safe? And they're quite surprising, I think, for us designing the swarms or the drones behind the scene. But it's encouraging that they're not freaking out. I guess that's my first reaction. So they thought that UAVs were safe, that they were effective, that they were beneficial, and that they were useful. So that's, brownie points for us. That they're not easy to use. That's the one that had a little bit more red to it. And that they have a number of advantages, that they have the potential to be cost effective, that they're an important investment. So they want their firefighting troops to have drones, and that they can help in improving operations. And when you put swarms in these questions, it actually doesn't shift massively red. So there is real potential in adopting these technologies. And these are 50 people replying. So it's a decent size sample. Of these, there's a mix of those who had used UAVs or had interacted with them, I'd say 50-50. Many of them had discussed UAVs, and then actually a lot of them recommended UAVs, despite not necessarily having them on a regular basis. And then in terms of uses and limitations, they thought they were really useful for situational awareness. The remote control ones that they have, they basically throw them in the air and then use them for very short missions to see something about the fire or the environment in which a fire might be happening. They thought they were useful for search and rescue, probably more the search side, fire monitoring and prediction, incident mapping and planning. And then delivery comes a little bit later, probably because they're not used to drones that have this type of cargo capability. And then the limitations are the weather, the endurance, the payload limitations, that they can't carry things. And so these are some of the things that we're trying to address with these bigger drones. We also asked them about their current use of it. So they typically just to understand a little bit more about the use of these drones within their settings and to understand current limitations. And in these focus groups, we really had them focus on huge areas, not a fire on a building, but California as a scale. And so how would you, the firefighters, monitor a high-risk area and engage a fire before it's impossible to stop it? We gave them an example of an algorithm that might work for that, which is our tiling algorithm. And what came out of that is that UAVs are already offering a lot of benefits, so they like them, which we also saw in the questionnaires, but they feel limited by regulation and by technology. So the drones aren't yet doing the things that they think they could be useful for. They think swarms are different than the individual robots that they're currently working with, and then they can be used as a proactive tool instead of just a reactive tool that you send in the field when fire has been declared. and that there's a real need and concern around how do you train people, how do you make it easy to use, how do you make it safe, how do you ensure there's no risk, especially if we're dealing with larger aircrafts. And then we did a Wizard of Oz study, which means we had them design interfaces and we tested them. And so we're currently writing this up, but this is what came out of that interface design. Instead of what you saw before, now we basically only have a giant map with drones. They're color coded. You can see their state in the bottom, in the left corner. And in the bottom, you get your swarm commands that are very streamlined. And this was exciting because just last month, we went to the field in Cornwall here in the UK. This is Lucio and Georgios from the Swarm team here in Bristol. And this is the Ultra behind them. It's the Fire Ultra. It's all, you know, nice fire colors from the Lancashire Fire Rescue Department that we work with. And this is the interface. And what was fun is we didn't use the interface. Like last time we had to give it to the company because it's their drone and they needed to really understand the safety of that system. And so it's very streamlined, very sleek, and they controlled all the swarm operations from their side during those trials. And what was fun is that one of these algorithms is a random walk, which sounds silly, right? Easy. But it's quite different for them to click a button and for the drone to do a random walk for them. It's not like a waypoint trajectory in a map and a very clearly planned system. And so it takes a little bit of to-ing and fro-ing to how do we get these swarm algorithms up on the drones? And so really through these trials, we're trying to explore what people are comfortable with. And so this has now led to us joining the XPRIZE in Wildfire Autonomous Response, which just announced their 30 team. So we'll be part of that over the next couple of years, I hope, but at least until 2025. As part of this effort, there's also a question of how do we make these swarms trustworthy? I told you that random walk. That sounds, a swarm engineer, does a lot of random walks for all sorts of different area explorations. But do people trust random walks? And so that's going to be important going forward if we want these swarms to be used in reality. And there's a number of things we've started to explore. One is thinking about what questions you ask to make a swarm safe. Is it ethical? Is it legal? Where's accountability? Can the individual cause harm? Can the swarm cause harm with its emergent properties? Can it be hacked? And then we've drilled in actually in this fire scenario to try to understand, okay, what happens in terms of do people trust drones? Do people trust swarms? What do you do if you see a barbecue fire? Should it extinguish it, or should you always ask consent to extinguish a forest fire? If swarms have cameras, do they keep all the data on board and do all the edge computing to avoid all that data from around the world being fed to a central system? Or do you need that central feed to be able to feed back to the firefighters? Probably a balance is what you need. And so really walking through what the risk is in terms of ethical aspects, but then also thinking about more systematically different areas that are important to make trustworthy systems. One is the swarm properties. Okay, maybe they're more efficient in some cases. Maybe they're more robust, more scalable, more adaptable. So you might think that makes them more trustworthy, right? Because your system continues to work even if you have a robot failure, or even if you change your environment, or even if you add robots or remove robots. So that could be trustworthy because it keeps working in all these situations. But if you see a robot failing because it can, does it make it less trustworthy? If you add lots of robots, does that make it less trustworthy? If you can, if it changes its behavior every time you change the environment, is it less trustworthy? Because it's a little bit more unpredictable than those other systems. So we don't know is the answer. We don't know if that makes them more or less trustworthy. And so we've developed measures to think about swarm properties so that we can address this in a more metricized way. We've also been looking at how we can control swarms, so using machine learning, but this time not just to find an optimal behavior, but find an optimal that meets the requests of the operator. For example, they might prefer to make a safe system over a very fast system. And so can we give them that control and then use things like map elites or artificial evolution to automatically come up with a library of solutions the operator can choose from? We need to understand what people are comfortable with. So on the left is one of our swarm algorithms. On the right is one of our tile algorithms. Which one do you trust more in terms of how they behave? Do you care? Do you just want to see the score at the end that says, I've covered 100% of the area and caught all your fires in 10 minutes? And that's something, again, we're not sure. And then in terms of how you specify, verify, and validate these systems, we've been working with Kirsten Eder and her team to really take what the machine learning community has been doing to verify and validate their systems. Similar problem, how do you learn, verify a system that learns? Here it's how do you verify a system with emergent properties? And usually what you need to do is be able to specify the system. So put what operational guidelines you're happy it works with, and then do a mix in our case of formal modeling, low fidelity simulations, high fidelity simulations, reality, and looping through these different states. I'm going to end here soon, just to say that this is one thing that really opened our eyes was that there was a workshop at ICRA in Japan recently on breaking swarm stereotypes. And what we were aiming to do is say that probably the sweet spot is in the middle. So swarms, typically we say they're fully autonomous, but maybe they need a bit of human control. Often we see they need large numbers, but maybe sparse swarms are also really useful, especially for environmental monitoring. They might be incapable or efficient agents, or maybe actually we put a lot of computation and brains on those robots. We think a lot about homogeneity, but maybe heterogeneity also gives us a lot. Moving away from the local sensing only, or when it's useful, to also considering more global exchange of communication. And so even though emergent behaviors are the core of all of this, can we make them trustworthy and safe? And so I think all of this is a really nice bridge actually between the multi-robot community, the swarm community, the human robot community. There's a lot to put into this. And with that, I want to thank my team. And in this case, I mentioned Windracers quite a few times. So I also wanted to shout out to them, and happy to answer any questions.
Okay, any questions for Sabine from the audience?
Am I audible by the way?
We will find out, and if not, I will just kind of repeat it close to the microphone.
So my question was mainly, given that all of these environments that we work with, these natural disasters and firefighting stuff, they come with inherent uncertainty, right? That's the characteristic trait of such environments. And given that this uncertainty, do you see in field robotics people who are at the front line using more of those structured algorithms which are deterministic, more rigorous planning strategies? Or do you see more of rule-based or learning-based strategies gaining some potential because they're inherently inexplainable and you don't want to rely on them, right?
That's an interesting question. So I could hear, first of all, thank you for your question. I'm biased because I'm a swarm engineer, but when we go to, so for example, the random walk seems really silly, right? But it'll always do something that has a potential to be useful. And so when you really want to go very quickly into the field and put something in the air, you probably want to be able to choose your strategy. I think that's the fundamental thing. You want to be able to pick whether you take a deterministic approach or a very swarmy approach, depending on how things are going, but depending on how messy things are. The swarm rules, I personally think that they're more adaptable to many different types of environments, but I don't know how comfortable the firefighters are going to be deploying them. So I think that's just, it's going to be a balance probably between the two of them. And so when in our interface, you can choose between tiled, for example, or random. And we did the random, it always found our simulated fire and all of that. And then they kind of gain confidence. And so they're going to have to play around with these tools and understand which one works in different situations. And I think that's kind of nice because the way we've put this is that they're the firefighters. And so, for example, through our trials, what we learned is that they really want to control the drop strategy. They don't want the drones to decide what's the best drop strategy because they're the firefighters, right? And so they want a feed of the fire, and then they want on a map to say, okay, this is how you're going to drop it, following this line with this wind, because that's their expertise. And I think it's going to be a mix of all of these. They might be happy for a random search or something that's very reactive, but at some point they want to have control of the thing that they care about as firefighters. Yeah, we'll see.
Do we have another question? Yes.
Thank you for the great talk. I was wondering, so you briefly mentioned something about a swarm of drones releasing pheromones. Can you talk a little bit more about that and what that's used for?
Sure. So that's one of our search strategies. We've used that in past algorithms as well, but for this one, basically the robots deposit pheromone, which is just a bit of information on a map. So they'll say, I was here, I was here, I was here at a regular rate, depending on where they're moving. And that gets uploaded to a map that is shared across the robots. And so as a result of that, each robot has a sense of where they were. So it's like a track, a virtual track on a map. And then they repulse from that pheromone. So it allows them to avoid going over pheromone that they've already, or areas that they've already visited. And pheromone, like in nature, evaporates. And then that allows you to have a dynamic map so that you can revisit places on a regular basis.
And maybe one last question. Yes.
Yeah, I have a question. You talked about that you create different options for the end user to choose from, which is a very interesting topic. I work in a similar area, but I'm wondering, how do you handle the complexity of a swarm system that you can effectively communicate? Like, what is the system doing to an end user so that they can give effective feedback, or how can they choose from all these?
Yeah.
Imagining many options you could create.
So in the worlds of artificial evolution or map elites, when we're trying to automatically optimize these systems, you need something you can measure. So for example, when we had them choose what they care about, there was safety, there was robustness, there was scalability, there was performance. And so those are all numbers that we can measure based on some of our metrics. And so we can, as a result of that, get a library of different behaviors that optimize those different features or trade them off. And then what you would need to do is give them those numbers so that they make sense. So we drew a spider grid diagram so that they can see, okay, my system is safer, but not as performant and maybe not as green or something like that. And so you can see using visual spider diagrams, the performance, sort of the score of how good that system is based on the characteristics that the user cares about. But then you select one or three, and then you have to watch them. And then there's like a human element of, okay, I know the score, but am I happy with this? And then that's sort of the thing that allows the operator to be like, okay, I like this. So that's one way to do it. The other is if you really want it to work, because I don't think they would do that on the big drones, then you need a pipeline to verify and validate and test it, like batch test very, very rapidly so that you gain confidence that your system is good enough, not just eyeballing it based on a video.
Okay, thank you so much, Sabine, for
Thank you. Have a great day. Bye, everyone. I'll try to stay online. Bye.
If you have any more questions for Sabine, just send her an email. Okay, then
Yeah,
we
we'll move to the next talk. It's a Skybrush tutorial presented by Gábor.
Hard name, Vásárhelyi, yeah, thank you.
He's a senior physicist, engineer, programmer, and also a visionary. He's the CEO of the Skybrush company. He has wealth of expertise in swarm robotics, autonomous systems, has background as a senior research fellow in EE, Department of Biological Physics, and he has made a lot of contributions to make engineering for different kind of swarm system. And we're pleased to have him today to make a presentation on his work.
Thank you very much. I will try to set things up quickly. 1 second. Okay. Yeah. So, and I have to connect to the Zoom, right?
that would be
Share
nice
the-
for the online.
Okay. Okay.
And there is an HDMI for the laptop you want to be.
Okay. I brought two computers with me, but I will give the presentation from the first one. And okay, so I'm already in, and then how do I share the screen?
And then at the bottom, click share.
Share.
Yep, perfect.
can you see it already? Is it visible online as well? Okay, so thank you very much for this invitation. I think it will be a really interesting workshop, and it's actually already are. It is interesting with Sabine's very nice talk. We have started this swarm business back in the old times, maybe at the same time when what we heard about from Sabine from the other talk. I started my work at Utrecht University, and there we founded Colmot Robotics as a spin-off company back in 2015. That was the first time when we made our first 10 drones fly in the air. It was a little bit after Sabine's work, but it was not fixed wing, but multi-rotor, and it also got a lot of international good feedback. So we were enthusiastic that we will be able to do something with the swarms. And sorry, I have to... Okay, great. And so we created this company just with the vision that swarms one time will be useful for some things. And it's owned by us researchers still. We don't have investors in it, and it's a very research and development oriented company, but we have commercial income as well with from drone shows, from precision agriculture systems, and now we are starting to move into a little bit to the dual use of the swarms, which is kind of a hard topic, but it's getting very hard to avoid, unfortunately. And we sell mostly software related to drone swarms, but also design software and hardware systems, and sell together with partners all kinds of systems where swarms are very useful. And we were talking about this with Martin, who will have a lecture as well soon, that as we are coming from the research industry, we really believe in this open source business model. So we are trying to build up a company in which we are already not researchers, but working for the company, but we would like to share many things from what we are doing, and we would like other people to use and grow this common knowledge as much as possible. And of course, we were inspired by this beautiful thing, what already has been shown. Actually, the name Colmot comes from collective motion. That was the acronym of the first European grant that Tamás Vicek has won in 2009. That's when we have started to work with drones and collective motion. And probably in this room, everybody knows the Vicek model. Tamás Vicek is the professor at the university, at the department where I'm coming from. And this was probably one of the first articles that used non-equilibrium statistical physics for describing biological systems of swarms. And since then, it's really a different new scientific trends, and whole areas are built on this concept that you can have agent-based swarms doing all kinds of things with complex agents and simple interactions between them. And in 2020, Tamás won this Lars Onzager Award, which is in statistical physics. It's a very nice award. And next year, the Physics Nobel Prize was given to Giorgio Parisi, who was also working in this active matter stuff. So it's really a well-known research field by now. And we have started also with many biological all kinds of systems where we were studying the collective behavior of different animals, thermaling birds and migrating birds, even little ants and rats in the labyrinth, etc. Some of our publications are still ongoing, and from that we have managed to publish over the last decade a series of very nice papers related to drone swarms, where we were try to apply all these biologically inspired flocking models and mindset to real drones. And I collected like 4 milestone publications here, which came out from our labs. The last one is from last week. We finally published our latest publication with 100 drones flying out, doing like really autonomous drone traffic. And it's what is really interesting, like Sabine also told this word emergent, that's what you have to face when you are bringing the system into larger and larger amounts that or So to scale up your system, you always get emergent behaviors and emergent all kinds of properties that you didn't expect. So this scaling up our system from 10 to 30, 50, and finally 100 drones is really like a 1 decade long journey in the research with a lot of going out, testing and failing and coming back. So you probably all know that working with large firms is really, really hard. And of course, there's a lot of reality gap. That is something that you have to face. You can see it from the fact that the simulation was always ahead of us. So we can simulate now 5,000 drones doing very nice things in the air, but having 5,000 drones is much harder to demonstrate on the field. And the two basic building blocks that we identified for this large-scale swarm movement was flocking and traffic. In flocking, you have the synchronized movement. In traffic, you have very individual goals, but you still need to coordinate in the same airspace. And we believe that all kinds of swarming applications can be legoed out from these two orthogonal building blocks, that you either cooperate with the others and do something together with synchronizing motion, or you just discuss how to go and how to resolve the conflicts, but you do your own thing. And if anyone is interested, you can find some details about the publications there. I'm just showing 2 short videos about these 2 orthogonal directions. This was the largest flocking system we have made in 2020 with 50 drones flocking. You could see it was only like a few tenths of a second before they found a collective decision where to go, and this algorithm is based on kind of an adaptive leadership behavior. When all the drones who are in the front and seeing the obstacles and the walls, they have more information about the environment, so the others trust them as some kind of experts at that moment. And then this swarm level averaging of the velocities is kind of weighted with all the ones who have information, they get more weights. I wish democracy worked that way, that all the local experts are giving more weight to a decision. But on this system, this is very, very efficient. So we could solve this with really 50 drones out on the field. And the publication from last week shows like a system with 100 drones, which are doing autonomous traffic, all self-organizing, communicating with each other. This is really something you can never do with 100 pilots. So it's really crazy to watch on the field and just pray when the first accident will happen. But actually it worked. And of course we have realistic simulations. So we simulate everything in advance and then raise the safety parameters to make it work. But we have some algorithms that are combining predictive motion planning with the local swarm level interactions in a way that the whole thing is kind of group optimized, and then you get very nice behavior with that. And the drones we have built from these are made with the same recipe over the last decade. So we have drones from the Pixel family. We put an onboard companion computer, and then on them we tested all kinds of communication things. The only thing that is not autonomous is that we rely on GPS or GNSS positioning. So we didn't go into the jungle of visual perception and computer vision. Martin is much better in that, but it would have been too much for us. So we were focusing on the swarm aspects really, and we are using for the low-level flight controller, we are using different controllers that are open source, for example, the CrazyFly system or the Ardocopter outdoors. And we have a high-level swarm controller called Flock Control that is on board and doing the communication with the other drones and giving all the instructions to the low-level controller on board where to go. And on the ground, we have the Skybrush system I will talk about more. And with these intelligent drones that have like an extra computer, as a first use case for the company, we have started to do drone light shows back in 2015. Then it was really a new thing, and we were the first to give a drone show in England, actually in the Buckingham Palace garden for Queen Elizabeth. Back in 2018, we were the first in Taiwan to do a drone show and really had this pioneering work. But then obviously these huge companies who became the competitors, they took over this field. So and our drones were not optimized for the drone shows. They were more intelligent, and all this swarm level intelligence that they were aware of, they were not used in the shows. In the drone show, everything is pre-programmed, so it's only like a coincidence that they move at the same time and in a synchronized way, but there is no interaction between the drones at that level. So we try to focus more on selling the software itself with which we design the shows and executed the drone shows, and that's what we call Skybrush. It's coming from this drone show modality, but actually it's a more general framework. And it has basically 3 different parts. The first thing is kind of related to the drone shows. We have Skybrush Studio and Skyscript Studio is like a plugin inside Blender, which is an open source design or animation tool, and it's specifically dedicated for drone show design. So in an animation software, you get all kinds of buttons for operators that have the mathematics behind the scenes to create automatic transitions for you from one formation to the other, create the return to home, the takeoff of the drones, the takeoff grids, all kinds of light effects, etc. So it's very easy to work with this. It's an open source software component, and I think it's kind of popular. We like to see that many users are using it throughout the world. We also have like a script-based, like a Python-based language for creating drone shows. It's a very nice, for a programmer like me, it's very cool to have like a code-based form of artistic expression. So if I have an idea in mind that I'd like to see something on the sky, I make code and it will be on the sky. It's a very good feeling. We really like this. It's not released yet, but it will be released soon. So this is kind of for drone shows, the design and validation phase. Obviously, you get all kinds of real-time checking in the design phase when the drones are too close to each other, or you want them to go too fast or things like that. How do I go? Okay, so the next phase is when you validate your drone show. We have a visualization phase for that, where you can, in 3D, you can take a look at your show and create formations and go around your mission. You can generalize this to any kind of mission that is pre-programmed. So if you have, for example, this tile-based thing, then you can replay it in before the actual mission and see which drone is where. You can check the velocities and then all kinds of altitudes if they are under the limit, etc. So, but this is also mostly for drone shows, and then the execution phase. For the execution phase, we designed another software component which is called Skybrush Live and Skybrush Server. The server is the backend, which is a very general Python-based modular and extension-based code base, which takes care of the communication with all kinds of drone systems. You can plug in DJI drones or CrazyFly drones, or helicopter-based drones, or our own flock control-based drones, whatever you want. You can attach RTK base stations, all kinds of communication modules, etc. And the server takes care of getting all the information and giving out the commands to the proper drones, and then it communicates with a protocol that we designed with the front end, which can be like for one client or many different clients. And this is Skybrush Live, which is written in TypeScript and JavaScript, and it's like a user interface dedicated for swarm level missions. It has many functionalities that are for drone shows, but it's much more general than that. And basically, it has all the mindset and the efficiency that we have designed for these large scale drone shows, that we were needing all the automation and ideas. So it's really a software that we are using in our scientific experiments as well under our drone shows, and it's also open source. So many people are using it. So open source is kind of an exaggeration because it's an open core system. Many of the things are really open source. So we are based on open source firmware, the CrazyFly and the Ordocopter firmware. We have our own forks that you can find on GitHub, and they add some extra functionality to be able to be compatible with Skybrush. We have Live and Server as the ground station, the swarm level ground station that we use. We have this Flockwave protocol that defines the communication between the server and the client which is also open source, and I think it's a very general and human readable, easy protocol. I think we are giving out high quality code. It's very transparent and modular, and we try to make it very well documented. And we also have a Discord server where we have a really large community with more than 1,500 people by now, and it's kind of active and really it's an expert discussions are going on there, so it's really a lively thing to be on the community server. And on top of that, there are some closed things that we didn't give out so far because we need to earn money from something as well. So we have this swarm level onboard control that is a proprietary code. We have some applications or extensions for the server that are for different applications for different products that we keep for ourselves, and of course pro users can get all kinds of custom solutions and VIP support. We open sourced this system like a little bit more than 2 years ago, and it has many forks and end users, so it's going well. And first, the first users were from the drone show industry, and we were very happy to see that with our software, many users could use much more drones than we ever had. So we had drone shows from all over the world that were designed and executed by Skybrush. We also developed with other Hungarian partner, hardware manufacturer, we developed a spraying drone, and which will be extended into a spraying drone swarm soon. It's coming out soon, which is very good for intensive agricultural spraying. It's fully autonomous, has all kinds of lidars and radars, and checks the environment, follows the terrain, and it's very easily programmable to do what you need to do with it. And we are taking part in Hungarian consortiums in big grants for making drone swarms for reconnaissance missions for dual use. It's really like a academic funded project as a kind of an introduction to reconnaissance in general. And what we have created, like we face the problem that we have this swarm kind of so we work with swarms for more than 10 years now, but we really don't see that many applications coming up. We wish there were more, and people don't have drone swarms yet. So we created this software in the loop simulator where you can actually check out and see what the swarm can do. So with the simulator, you have the Skybrush backend and front end working fully functionally. You have multiplied onboard systems with Arducopter and flock control. They are running in parallel. How to have the swarm? We integrated the transmitter. I have the gamepad here for that. And we integrated also an external flight simulator, like anything can do from gazebo to air sim or whatever we want. It's just an extension to have a 3D virtual environment for that. And then with that, you can integrate the perception part as well. And it's a very good tool to be able to test. It's a new thing. We have it for 1 or 2 months working at some partners, and we are very happy to share it with some of you if you are interested in trying out our system. And this is how, for example, one mission looks like in Skybrush. You have the drones, you have all the information from them. You can set up swarm level missions or control the drones individually, send them here and there. Drones have their own autonomy, so wherever you send them, they avoid each other, avoid obstacles that you define on the field. And this is basically for this closed level swarm behavior. So not when your swarm is really spread out over California, but when they are at the same place and have to interact with each other and go and coordinate their motion. And yeah, so I have one of these slides. Just if anyone is interested in trying out Skybrush, it's obviously it's open source, so you can find it on GitHub, and we are very happy. You are welcome to use it, and we are open to cooperation with that. So any kind of R&D project that we can do together, we are focusing on giving out products that are based on Skybrush, and with hardware manufacturer partners, we can bring together something to the product level. And also, if you feel that the simulator is useful, then this could be a use case. And we are also like kind of a small company, so we are also looking for strategic partners to who have other types of competencies to put it together, accelerate the development. And I don't know how much time I have. If I have 5, maybe I can answer the questions, and in the meantime I can change the computer and then show the simulation in real. So if you have questions, please go ahead.
Yeah, good question. Describe the setup, I guess, between like when you show up at the site with a box of uncharged robots to the point where you press the go button and they take off. I guess what are the kind of the steps that are required as that setup?
So we are trying to make this as automatic as possible, and this is one of the take-home messages from our many years of experience, that when you have a lot of drones, I don't know how. Sorry, how can I? Zoom is not working on this laptop. So it's always a lot of problem to work with many drones on the field. You have to do everything on each drone one by one, and the more automation you get, the better it is. So we are trying to make our software as automated as possible. So basically, once you put the batteries on all your drones and you put them out on the field, it's only a few clicks. You go over like a checklist, and with a few clicks you can design your stuff and upload to the drones and press start, and then they do everything on their own. And since we come from this decentralized mindset, we are trying to define everything in a way that you upload the mission to the drones in advance, and after you can kick your ground station, and then you don't have monitoring, but they will do what they have to do. So that's what I wanted to show here, to how to go through, but unfortunately I cannot start the Zoom meeting, but I might be able to share at least the ground station. So do you have 3 minutes to go through this? So basically, if I start a simulator, it will run all these Ardocopter and flock control instances in the background. Okay, so on the top you see the AirSim simulator, which is the flight simulator. Here, this is the launcher for all the different drone onboard software. This is the Skybrush server that is running, and on another tab you see the individual drone brains and all the logs that the drones are producing. And so this is the backend that is running all the things in the background. You have this AirSim integration in which you have all the drones, and you can have like a first-person view from the drones, and it's a rendered environment. And then you have the front end, which is Skybrush Live, where the virtual drones are already there. We have a transmitter. If I press different buttons, they change flight mode, and I can start and then navigate from this as well. And the way you create a mission is very easy. Like, for example, you select all the drones, you select this polygon, for example. I already created, this is Delft University. You have some obstacles here, what you can easily define with tools on the side. You have a plan button and select the type of the mission you want to make. So for example, this reconnaissance mission, all kinds of parameters you can set up. This is a swarm level mission, the same kind of, like the one we have seen with Sabine, that drones are doing some kind of random motion to find something. So you just create a mission, then you have all the mission items here on the right. You just press upload, the mission gets uploaded to all the drones. Then you put the drones into the mode where they have to be, and just arm their motors, and then they will do the mission. So basically, it was like 1 minute. You create a polygon, you tell the drones what to do, and then they will fly and show and go on their route. And the drones are, so this is a swarm interface, so you can give commands to the drones together, or you can control them individually. So if I want to, for example, this is drone number 1. If I want that drone to come over here, then I can give individual commands, and they have onboard autonomy, so the pre-programmed obstacles will be avoided. They avoid each other as well with the onboard autonomy, and now this is an algorithm that is telling them to just go over this place in a random walkway and try to do some kind of surveillance. So you can give individual commands to the drones, you can give swarm level commands, you can make all the drones come home, and then they will turn home and come home, and there are all kinds of other missions that you can provide with different extensions that you write. So for example, we have seen this tiled kind of sharing of a territory. You can have the same with so this is, for example, one kind of scanning mission, which is divided into 5 parts. It's not tiles, but equal parts over the mission, and then you can upload that to the drones, and then it will be a deterministic stuff. So basically, the type of mission that you want to create is in a server extension. It's very easy to code, and then you can interact with the drones and upload. So basically, that's all. I wrote this thing to be able to play with it a little bit. So you can train how to fly a drone. You can try out all the swarm things. It's not like as it was said by Sabine, it's not very trivial how you control many drones with a human operator, but you can try how it feels like to have more drones moving on your commands, how to select drones and control only that. So it's all these simulator is also a good tool to be able to practice all this swarm level operation that needs a very different mindset from just having one drone controlled. So basically, that's it, and I will be here with the computer, so anyone interested can try out here.
Miguel and Rafael, do you have any more questions?
Yes.
Software, like you have talked by the way, but one thing I was wondering, a lot of companies and research institutes work with the swarm level stuff, but like they create their own middleware for communication and just publishing software. I was wondering if you experimented with ROS a bit, and did you find any bottlenecks of why you aren't using ROS, or did you not try it? Like
we found ROS to have too much overhead. We were always focusing on making as many drones flying as possible with the minimum of communication that is needed, and we rather wrote our own stuff similar to and parallelly to ROS. Many of the things we just rewritten, but in more efficient ways than ROS. And by now, I think ROS 2, and there are some things that are really advanced and nice. And then, for example, if we ever did computer vision, that I think we would do it in ROS, because that's really strong. But in general, it was just too much overhead for us, and for this, and also not reliable enough. So it started as a research tool, and back in 2015 we already had to provide like very reliable systems for live events, where like in the largest events in a big national holiday, there are like 500,000 people around our drone shows. So we really have something that is working very accurately and precisely, and we cannot afford to have a research tool in that tool chain, because that's a hazard.
Okay, thank you, Gábor. Yes, I think that's right. And as Gábor said, during the coffee break, we actually have like this room, and there's also a table kind of outside that we can kind of discuss and show the various systems as well. And now I have to do the introduction because you can't introduce yourself, but we have Miguel and Rafael from the Polytechnic University in Madrid, and they are the developers of Aerostack 2 and co-organizers here. So, thank you so much.
So we are from the Polytechnical University of Madrid. We are in the Computer Vision and Aerial Robotics group led by Professor Pascual Campoy, and we have been developing Aerostack 2 for more than 2 years now as the tool that we use for making like drone research, but also trying to get into some industrial applications. So in this tutorial, we want to like not to make a super condensed explanation about all the framework, but just the flavor that it has. And if you want to develop a swarm application from scratch, learn what pieces you have to put together and how you can start with our framework. So we will have a small introduction about the framework itself, and then we are going to like not coding, but something pretty similar to what you should do in order to make your own like swarming example. In our case, swarming is not about 100 drones. We are going to make a demonstration with 3, but I think the ideas is what should be like led for this talk. So Aerostack 2 is an open source framework that is based on ROS 2, and we wanted to be used for design and develop and deploy very different type of aerial robotic systems, and this was created from scratch, but based on all the lesson learned from a former framework that we had in ROS 1, and we have been using since 2016. So I want to start with why do we created this framework. So in our lab, we have very different type of applications, and we want a framework that was flexible enough for being able to reuse different pieces that we have developed for some things into other with this modularity advantages of picking these blocks. We fly different types of drones, from the very little ones for research application or for demonstrations, up to the big DJI industrial drones for different kind of industrial inspection operations. We wanted to be able to handle multiple drones, and we also focus on being able to, because we have different students, that we want them to be able to make their own things and like get in contact with making real applications. So we also want to create a like easy to start way of developing different what we call aerial missions. We want to test everything safely because drones are dangerous, and if you cannot validate well in a simulated environment, then things can get very dangerous. And we also require to support both indoor and outdoor operations. So we will get like piece by piece after, but just a glimpse on the architecture. We go from the lowest control, which is commanding the hardware. In our case, we have like what we call the sensor actuator interface, which is meant for communicating with the different hardware platforms. And then we build up on top of each layer by having a higher level of abstraction about what is going on. And the idea of the framework is that you don't have to use everything. You can just pick the pieces that you want. For example, you only want the interface, so you can just use this, or I only want to give a motion reference and all the planning I'm going to do on my own. And as we work with ROS2, we have like this distributed communication channel, which is more tricky that people of ROS2 sells to everyone, but we are able to communicate with some with some tricks. So some different use cases that we have been done with the framework. This is like a small choreography of 3 crazy flies. There we have like 2 drones that has to pass through different ways, also like in a coordinate way. And these are like more the lab and the easy examples. We also use it for research. For example, in that case, this is a bug explore algorithm for exploring unstructured environments using minimal sensing, like the crazy flight drones, and we rely on the benefits of having this framework for start with just the thing that you are wanting to research on, and all the rest of the things are well tested and can speed up research a lot. And also we have like real world deployment of, in this case, this is a photovoltaic plant inspection, and we are able to like plan, monitoring, and also like this is a fancy visualization about what the cameras of the different UAVs were recording. So as you can see, we have like a lot of different kind of things. So how should we start? For this workshop, we decided to create something new and test what we are going to like show here, that if it's as easy as we want to present here. So we formulate a problem that we have not coded yet, and it's a simple system that we will have one leader and n drones that are going to follow them in like the n+1 drone is going to follow the nth drone, and in that case they are going like only taking care about the drone that they have in front of them, and they also shall keep a horizontal security distance, because with this crazy flight, if one flies in top of the other, the air can get disturbances. And the leader, we can teleoperate it or just have a predefined mission. So for the tutorial, we have created like a step-by-step guide for being able to reproduce all the content that we are going to present here, both in simulation and in real world. So we'll start with, okay, I have this framework, and what should I do first? The first is pick the pieces that you are willing to use on your application. In the first case, you have to decide which are the aerial platform that you are going to use for this application. In this example, we are going to use Gazebo as the simulator, and in our framework we have created a easy way for launching Gazebo simulation. You just type this world.yam file, you put the name of the drones and the positions that you want them to start, and then we have the Gazebo platform, in which you load this file, and it's able to search for the Gazebo bridges that they have to implement in order to make the simulation connected with ROS2. And for the Crazy Fly, we just have to launch the platform of the Crazy Fly, and you can add the different parameters that you want for each drone, and the whole the launcher is going to take care about which namespace had you have declared and create all these nodes. Then when you have decided which is the platform that you are going to deploy the system, you should decide which is going to be the controller and the state estimator for this application. In this case, we have created like a plugin based strategy. So you can launch the controller, which is like a plugin loader that takes care of the plugin that you specify, and it's able to connect it with all the pieces. So if you want to develop a new controller, you just have to code a plugin and you don't have to think about how the rest of the things interact between them. And something similar happens with the state estimator, which is the part that also takes care about generating the TF3. And for this application, we will use the ground truth from the simulation, but for the real world experiment, we are going to rely on the odometry that the CrazyFly provides us. And on top of this, we have what we call behaviors. Behaviors are an extension of ROS to action that allows us also to pause them, resume, or modify it. It's an encapsulation of of an action that you want the drone to do. In this case, we have like pretty simple actions such as takeoff, go to points, follow path, but they can be as complex as you need. For example, you can add behaviors for perceiving, for example, detecting arucos or whatever. And this like have all the mission using these behaviors is the part of the plan execution and control. So the idea is that you just create the sequence of activations and disactivations of behavior that you want in a mission, which increases the readability and also the explainability about what is happening on your system. So in this example, we have created two missions, one for the leader. The leader is just going to take off and go to the points like path facing. We have a Python API that connects the behavior calls with Python functions, but make it easy for people to start and to understand what is being happening. And for the follow drone, we have created what we call an aerostack module, which is just an extension of the drone interface. And we have created some code for following the previews, which is take record of the positions of the drone that you have in front of you and just try to replicate while being in a like separated enough to the previews. And for like checking that everything is running okay, we had first made some plugins for RVs to be able to keep track of the trajectories and have the reference command also visible. And we have a teleoperation tool that help us with even stopping if something goes wrong, but also to maybe teleoperate the leader and see how the other follows it. So I will make a real demonstration on how this works. I'll start launching the gazebo world with the there should be 3 drones if I find them. Oh. Now we have like the launcher that I have shown before, one from the platform, one from the state estimator and the motion controller, one from all these basic motion behaviors, and just for monitoring that everything is okay, we have what we call a terminal user interface for checking that the topics and all the information is running properly. It doesn't scale. No, it's not. Yeah, it's like pretty only for testing that everything is running as expected. And now I will just open the RBs and the teleoperation tool. And the missions for the follower. I will teleoperate the drone, so I click which drones I want to control. And if everything is okay, whenever I take off the first drone, the other are going to follow what the leaders do. And as you can see, it can just follow without colliding. And whenever one lands, the other lands. So with this example, we like try to show that the pieces that we have used are well known for everyone that works in aerial robotics. We have a platform, you have controllers, you have a state estimator, but you can just take this thing, and if you want to develop a new controller, you change it, and you can use all the other tools that are already available. And if I want to move this into the real world, what is expected is that I only have to change the platform, because all the logic and all the rest of the things shall be compatible with what we have shown on the simulation. So if we just place the crazy flies, okay, so I did the same, just I didn't run the simulator. And here I will not teleoperate because I don't think I'm good enough for not getting out of the motion capture area. So in that case, I will run the mission of the follower drones, and we had a pre-planned mission for the leader drone. So if you can see the waypoints that each drone is going to go. And now the first one is starting to move. And whenever they found that they are too close, the drone stops. And our intention with this is just to like show that people that are not used to, well, we have recorded everything just in case it didn't work here. We have like a more extreme, like more, operation in which Rafa just moved the drone crazily to see if the other are able to follow in the, like not so smooth reference as when you plan it with concrete waypoints. And yeah, we want to present our framework to show that it's easy to start with, even for people that don't have their own stack yet, people that have a lot of already working code, they maybe not find this framework as interesting, but I think that people that wants to move to ROS2 or they want to start making drones and or test algorithms like without taking care about exactly on which platform is going to be developed, we try to document our things in the best way we can, and we are about to release a new version with better integration of different platforms. We had a path planner, map generator. So I like also to acknowledge all the main contributors of this project. It has been more than 2.5 years of development, and if you work with drones and you want to give it a try and make any contribution on, it will be very good for us. So thank you.
Question.
Could you specify a bit or repeat maybe that what is, like from the algorithms, what is running on board and what is running on the computer in case of crazy flying, for example, in case of outdoor?
Okay, in case of the crazy flight, everything is run on my computer, but when we make, for example, the industrial application that I have show, all the computation is done on board. We have a Jackson computer on board, and the only thing that it's like the plan is generated in a ground station and it's sent to the drones, and then you only use this for monitoring or for taking care. The rest of the code is written in C++ in order to be as fast as as possible. And yeah, we try to make all the computations on board if it's possible. In this example, we also run some neural networks on board of the.
And so for this, use the GI SDK.
This? No, this is a custom tool that we have.
No, on board.
Yeah, the onboard SDK, yeah, or the payload SDK also. It's now available.
More questions?
Before you're releasing a new update, but before that update, it's like mostly for crazy flies?
No, we have DJI OSDK, which is not maintained, and in this version we have updated with the PSDK. We have PX4, but from the directly communicating using ROS2, but we have added the map link because we know a lot of people use ArduPilot, and we also have added this. We improved the camera from the Crazy Flies and also the Taildraw DJI. These are and we in this version we only use modern Gazebo and we deprecate Gazebo Classic.
Any more questions? Maybe to relate to the previous question, what was your experience with using ROS2 versus not having any middleware?
In our case, we found tricky to use ROS2 at the starting, even because if you don't know how it's working under the hood, you have a lot of wrong things that doesn't work and you don't know how. for example, you have a publisher, you have a subscriber, and you run both, and it doesn't do anything. And I said, I checked the code 20 times, and it's maybe because there is some daemon process or some discovery issue that if you are not aware about how the DDS is working, it's a bit tricky. But after this, for example, for multi-robot system, we have used Xeno on top of the Cyclone DDS, and we are able to control exactly which amount of information we want from each like local network of each onboard computer up to the rest of them in a like pretty nice way in order to be able to just transmit the things that you are interested on. And with this making, or if this if I have like no computational capabilities in my computer, I can just put another computer running the rest of the code in the same network, and ROS2 is making it work without having to do anything more. So in my opinion, it's good, but you have to know maybe how it's working under the hood if you have a lot of issues.
Maybe also the question.
Like, so the hardware capability of the CrazyFly, how, for example, if you are forming a swarm of tens of robots, will Wi-Fi latency or Wi-Fi complexity?
I'm not expert about how they work, but I think it works with radio, and I don't know how much, how many CrazyFlies it can handle one radio.
Well,
but
technically for the swarming, it's you're the expert. Yeah, it's a separate. It's not Wi-Fi protocol. It's a separate protocol called real-time crazy protocol, or CRTP. So that is kind of using an NRF51 chip to communicate with each other. It's like our own in-house made protocol, similar to I guess SiQi or like other of those types of things. So yeah.
Okay.
It's quite quick.
Then it's time for some coffee. There will be kind of some more demos outside and potentially also inside. So
Yeah, for the preparation of the tutorial.
if you want to learn more about like these 4 stacks here, you can also come to talk to the developers. And otherwise, the coffee should be right outside, and we meet again at 4. Yeah.
That's an idea to.
I just propose it here, maybe.
Can you pause? Yeah, then I can do that, and I will. That's a wake-up call. So welcome back everyone to the Aerial Swarms workshop. So now we will have in the afternoon or after break session 2 tutorials and then 2 talks. And Kimberly and I will start off by presenting Crazy Swarm 2. And first, we can talk about us briefly. So I already introduced myself. I'm from TU Berlin and an assistant professor.
Yeah, so I'm a robotics engineer at BitCraze. We make the small little CrazyFlies. You already saw them flying. And we're located in Sweden, in Malmö, so right across from Copenhagen. So do drop by our nice flight arena and office if you would like, if you happen to be in Copenhagen. Yeah, and I used to study here as well. I was here for 12 long years in TU Delft.
Okay, and then so you haven't seen it. So Crazy Swarm is a word that has been around for a long time, and that's I think from 2016 was one of the largest indoor swarms with like 49 drops. I'm not sure all of that. And so maybe back then the more technical insights were that it's really important to put more autonomy on board. It was also one of these systems that really heavily relied on motion capture systems, did some custom frame by frame tracking and a lot of like low level optimizations for the radio communication to make it work. And it was widely successful in terms of just kind of looking at citations, but also people using it for different kinds of research. So just 2 years ago, I did some sort of analysis, and it was really kind of spread quite around. And so Crazy Swarm 2 mostly came around because Crazy Swarm 1 was based on ROS1, which was kind of discontinued. And so we thought we kind of start from scratch, since it's like a breaking change anyways, we kind of revisit it a little bit and try to figure out how can we make it different. Like many ROS packages out there, when they moved to ROS 2, they just added 2. And so we did the same, so it's still based on ROS, namely ROS 2. And the architecture is quite compact, I would say. So we have a kind of one server. The server is the one that talks to the drones over one or multiple radios. It can be configured, and there's different sort of backends, which we will also talk about a bit later, all with the same kind of ROS style API. There's still the option to use motion capture, although it's kind of not really baked in anymore before, so it's just kind of a separate package, which still has the same fun magic of frame-by-frame tracking that you can now use for all kinds of robots if you wish. We do have also a simulation. The simulation is not as special as you would think, because it's really just one of the backends. So it just provides the exact same ROS API and can be therefore used completely like transparently. And also from before, we had this Python library and we kept it. It's kind of fully compatible, except for the import statement that you need to change. But the old scripts should technically still run. And maybe what's kind of super special, talking also about the backends a bit more, is that we kind of teamed up. So now basically a university and the company behind the drones is working on it. And so right now, I guess the split is that I or the university mostly does this one backend and the company does the other backend. Okay, so the server is kind of maybe the most like the backbone. So it can be configured by what drones we want to connect to. We can use one or multiple radios, and we can do these normal things like logging, like streaming data from the drones, or setting a sort of parameters, which we will show in a demo as well. And maybe then we can get started with that. So we kind of have this fun little tabletop demo. And yeah, we can follow that. And I will just also show a little bit of the code tools.
Great. No Swedish ones yet, so you could just walk in.
Okay, so one of our major config files is this CrazyFlies YAML file, and it's like a YAML file, so it has a list of robots. The robots get these addresses. If you want to use simulation or any sort of frame-by-frame tracking, you need to provide an initial position. In this demo, we won't use it, so they're all the same. Each robot has a type, and then you can set settings for types, and then you can also set settings globally. And one of the settings we can look at, for example, are these log topics. So these are variables that the robot has baked in to the firmware, and they help us to identify what's going on. And so you can kind of group them together and also tell at which frequency you want to collect them. And you can do that at different levels. So you can either configure it globally in this all setting, and then all of them will bring the same data. You could configure it per type or also per individual robot. And it will just take whatever is like the most specific thing available. The other things you can configure here are parameters. These are settings that can change the behavior of your robot. Think about something like switching the controller type or switching the state estimator like we have here. And the same thing, we can control it on all different sort of levels. And just to kind of give you an example, should do tabletop demo. So when you run stuff, it will connect to the CrazyChoir. In this case, we use the Python backend, and it should technically show them here. So it doesn't have a because I disabled the post. That's right. And then what we wanted to show is that it really integrates really well into the ROS ecosystem. So one kind of standard tool in ROS 2 is this plot juggler, and that is used to just plot data, and then you can see this the topics for all of these robots. You have different topics. So we have 3 robots here on the table. So I can just select, for example, number 6. And say I'm interested in plotting something, and then the ranges were what I had configured, and then we see the values live here. We can also like drag it in and plot it, and then that should be kind of the front sensor here, right? So if it's out of range, it shows you really high values. So wait a bit till the out of range works, but then if I move my hand, we get these kind of nice live streams. So very kind of standard stuff, pretty easy to do. All right, and then the other thing I wanted to show is just the integration also of the parameters. So a standard thing is RQT. It should show us parameters. Yeah.
It's good to so that everybody can see them.
Yes, but once it shows us actually something.
Somebody said it was too.
It's at least not our code, right? It's crashing. Here we go. By the way, that's ROS 2 Jazzy, so it's the latest and greatest release, so we can't even blame it on old software.
Oh, well, wait.
That's good.
I'm sure it's just my laptop.
Yeah. That's the nature of trying the latest and greatest.
You're working over the ROS 2 versions? Like you're up making sure that it works with like all of them?
Well, this is the ones that are currently supported, so we also support Humble. And then Iron, I think is usually, it's soon out of
Yeah, we
end
don't
of
have
life,
Jazzy,
and then we will.
not Jazzy, I mean the Foxy. Yeah, no, I don't think, at least we haven't tried recently. But
Yeah, I think most people are using them.
yeah, oh, yeah, I use Humble all the time.
Okay, it's like super slow.
Yeah. Plot Juggler is great, but somebody would like to make a parameter version of Plot Juggler. That's it. But this RQT is a tool GUI by ROS.
It's also missing these parameters, right? Like it should be some other parameters here.
Maybe?
Maybe we just continue and then go back.
Yeah, exactly.
But then, I mean, in principle, what you want to show is that the parameters kind of show up, and then you can also, I could try this bit mask thing. Okay. So that maybe I have to show the drone. That will kind of change the LEDs, and the kind of turns off. Oh, back on. and it happens to all of them at the same time. So you have kind of this nice broadcasting behavior here that you can make use of. Okay, then we also do have some simulation tools. And so, of course, the goal of simulation is that we can test, that it also seamlessly sort of integrates. And our simulation was very modular. So in Crazy Swarm 1, it was really just a visualization tool. Here we now can have a lot of different backends that kind of simulates the physics. And we also have different kind of visualization tools. And so, as I said earlier, it's implemented in the same way as the server, so it has the same API. So everything like the graphical tools and the scripts will just work. It uses full software in the loop. So the firmware has Python bindings, and we use these Python bindings to run, for example, the controller exactly like it would run on board the firmware. It's one of these 40 simulators, basically, that are in the survey paper I mentioned at the beginning. So if you want to learn about other cool simulators, you can check out that paper. And maybe also just to give you a little insight how it works. It is fairly simple. So we have this config file over here. And there's like a section that is just simulation related. And so you can, for example, select your backend and the visualization tools. And then if we run it, that was fast, right? Because it didn't actually do much. It just kind of visualized the set point. And then what you can do, it was configured to kind of output an animation. And then you can also watch the animation, and you can kind of scrub it and like go to a particular point in time, pause it and go back, which is quite nice. Okay, and then if you kind of want actual physics simulation, what is very special is that we have a quite high fidelity simulation optionally. So one backend we have is actually using a neural network that tries to predict what happens when two drones fly very closely. Because it's high fidelity, it's also pretty slow, but I can show you maybe one result. So one way is, again, showing these sort of animations. And then what will happen is for the lower one is that it kind of goes down. And there's also other backends that can, for example, write out the results as a PDF, and then you get a page for each of the drones. And there you can also see for the lower drones that you get this weird kind of peak in velocity and also in position just because of the downwash effect. Okay, and with that, I hand over to Kimberly.
Yes, all right. So we're going to look a bit now to the Python API. I think we've seen it already in multiple forms already in previous tutorials. But perhaps you can kind of like use this also to kind of like see the similarities, which are actually the useful building blocks that we want to use in our to make it at least like this whole framework or scripting easier. So in case of the server setup is that, yeah, I guess we've already talked about that. We have a couple of command and logging topics. So the command topics are, we can control formatted to command, velocity commands. We can give it position or a full state control, but not all controllers are fully compatible with that. I think mostly manager and of course, like Wolfgang have already showed some of the logging topics, like
that you can customly add to the YARN file in order for it to get all of those, be able to log from different types of different crazy flights at the same time. But we also have some standards logging topics that it outputs kind of the logging in a format that other ROS2 packages would use, like odometry and scans and pose. Perhaps you can show that later, see if we can get that to work. So yeah, and that's also kind of like, also we have all the CrazyFly parameters. That's also something that Wolfgang already showed. And that's done for each CrazyFly, which is kind of a lot. And therefore it is quite nice to kind of combine that into some sorting scripting language, or we have the CrazySwarm Python wrapper that we would like to use for that as well. So the simulation that Wolfgang showed before was the downwash simulation. Of course, you would like to see that in real life. And you've also used the script, like the same Python scripts for those two crazy flies to go a little bit up and fly over each other, like the swap script. We can use exactly the same swap script for the real crazy flies too. So let's see if this will work. And how do you copy paste?
Maybe we show the script first.
Yeah,
just to get a sense of the flavor.
Yeah, exactly. So so this is kind of like how the what the Python API for the CrazySwarm Python script is doing. So you have here where you assign the CrazyFly 1 and 2 objects, and then you can say like all CrazyFlies take off, but you can also do that for each individual drone. Then per CrazyFly you can actually say like, you go to this position, you go to that position, and then here it's, you swap them, but of course, like, on different heights, or else they'll crash. The lighthouse positioning system is pretty accurate. So so that is, I guess you kind of got the general idea, right? So let's see how it works. We should be able to see the same thing as in simulation. Right, second CrazyFly demo successful so far, 100% success rate. Although now we're really trying the dynamics a little bit. But the means is that, you can use the same scripting language for simulation and the real things. Obviously, you guys know why it's handy, right? So we don't really have to explain that much for as well. I have to kind of look at as well on time. We can show a couple of applications that we can use, that we can show with the CrazyFly, but I think we first would like to focus on the fact that we're using the ROS2 framework to be also able to connect with other ROS2 packages, because that's kind of the strength, right? You don't want to recreate every let's say navigation technique or SLAM technique all over again. And that's kind of also the strength, is that we can use the CrazyFly server to assign one of these standards ROS2 topics like scan and odometry, and then we can perhaps use a CrazyFly, or an external ROS package that is actually meant for a different platform, and make it generate a command topic that can be wrapped for the CrazyFly to actually respond to. So what we are going to show now is kind of a swarm mapping example. We have multi-rangers on these CrazyFlies as well. So they're going to create, all three of them are going to create a simple map. And then we use an external ROS package, let's say, to merge those, let's say, those maps together to a swarm map. All right.
I should run it.
Yeah, I think so, but because I'm not able to copy paste it, but it's there. I was working on those.
This one, right?
Yeah, so now we're launching the robots to launch file. And then you can, yeah, now you can see them or not. Fully. Now you see them. Now you also see the transforms also in this map as well. So you have CrazyFly 6, 4, and 5. And yeah, we also have another node where we can control them at the same time. We're going to be a bit careful because we're not good enough to control them all at once, but we're just having a simple tele-op keyboard node. So then we can hit T. And they're just taking off. We set them at like different heights at least, so that the multi-rangers are not going to interact with each other. And then you see like the back generating there. Multi-ranger is very sparse, of course, so let's rotate it a little bit. And then you can kind of, yeah, slowly but surely do wonder what happens, what's happening with the other range centers, but you can kind of get the picture, right? Like, you know, they can do it either closely together or as it's meant to be, as the example that I also showed in our stack 2, move around the space and actually do the mapping collaboratively. But this is kind of like more of like a live demo, at least the mapping of this small corner. So yeah, now you know how this corner looks like. And don't forget the one. Yeah. So yeah, I think we have to kind of keep an eye on time. So we had one video application of another one.
That.
Yeah, we skipped that indeed. So yeah, that's kind of like we're coming now to the conclusion. So let's say CrazySwarm 2 is not perfect. It's still like in progress of definitely improving. We're dealing with a couple of connection link issues with the CPP backend. And also like the scalability of number of robots, like the 50 that you saw in the CrazySwarm 1 video. We haven't made that happen with CrazySwarm 2 yet, and we really need to do that. So, but you need a lot of robots for it. Yeah, so that's, and then also heterogeneous simulation as well. What did you actually mean with that? Was that different robots?
Yes, I mean, the whole goal of the ROS2 integration is that we work with other kinds of robots as well. Otherwise, we could skip ROS2 altogether, right?
So it's not only simulation, it's like, you know, in general.
In general, like for the rest, we have achieved it, but in simulation, not yet.
Yeah. And of course, like once we have definitely those co-connection stability issues figured out, then we're hoping to release it to actually be in an official ROS2 package and easily installation. The motion capture tracking nodes that you can use with CrazySwarm 2 has already been released, but would be like nice to do the same thing with CrazySwarm 2 as well. Yeah, so how to get support? Let me just okay, now how to get support. So like GitHub discussion for almost everything. CrazySwarm 2 has a GitHub discussions. So if you have any questions, it would be nice to keep it there so that everybody knows what kind of issues you're dealing with. We know it. We can kind of also reuse all the answers that we are giving you as. Yeah, exactly. And if you are confident in the code base itself, feel free to make a GitHub issue or even make a pull request because, you know, it's open source. Please contribute. Yeah. So this is the QR code to the CrazySwarm 2 project. And if you have any questions, please let us know.
Any question?
This may be somewhat specific, but in the simulation, do you have any simulation of like radio lag or any other like lags, I guess, like Vicon lag, radio lag?
No.
Okay. Okay. We don't either.
I don't think a lot of people really focus on that, although it is something that is very important in swarming. Yes.
We do have a simulation framework, an open source one, where we integrate all kinds of noise and delays, and we do it for 10 years, and it's very, very useful when you want to reduce the reality gap. So.
Okay.
But I must say, there's not a lot of these robotic simulators that we found for aerobotics that actually focus on this stuff.
Yes.
So that is very difficult to find.
Want to set up?
And it's definitely very important. Like I know that WeBots, the simulator that you guys are using,
we use a lot.
but they're one of the few actually. The robotics research simulators, but yeah, the QR guys are. It's very important.
That's essential to be able to scale because it's a very dynamic, like quality oscillations.
Yeah.
And those are not.
You do the same, right?
Yep.
That's cool. Okay. Then
Now, Lorenzo and Andrea is going to present their work on their tutorial on CrazyChoir. And hope it has another cool demo as we have done.
Yep, so. Obviously.
Okay. Okay. So we want to start with a brief introduction of our supervisor, Professor Giuseppe Notarstefano. And how you
hello everybody. Can you hear me?
Yes.
Okay, so I will soon leave the stage to Andrea and Lorenzo. I just wanted to say hi everybody and just few words about let's say the path that draw us to this day, basically to CrazyChoir. By the way, thanks to Kimberly and Wolfgang to involve us in this organization. I hope it's going well. I'm pretty sure. So basically, everything started when with our ERC project, the project Ops for Smart that I was coordinating. At some point, we had to do in one of the last activities, work packages that were experimental. We designed a lot of distributed optimization algorithms and also distributed control algorithms for multi-robot systems, and then Andrea, Testa, and another Andrea that at that time was working with us, they were carrying on these experiments. So we figured out that there are, as you can see here, a lot of very interesting scenarios that involve the communication among robots according to a network. Robots have to communicate one-to-one. And so if you think of like pick-up and delivery, as you see there, task allocation, but also surveillance as the applications that Lorenzo and Andrea will show, then we figured out that it would have been very nice to have a toolbox and infrastructure to do everything like that. And then I have to say that the inspiration was by Andrea Testa that you see there. He's really the starting one, because he said there is this very cool toolbox called the ROS2, and it's called ROS2. It seems just a small update, but it's really disrupted. It's really another thing. And for us, it's the best that we could have, because it allows robots or nodes in ROS to communicate one-to-one. So without passing through a central server. And so we started to explore it, and basically the first robotics toolbox started, so this Choirbot. And it was really ROS2 born, because as Andrea was suggesting, that was the key to allow the communication. And in fact, what Lorenzo and Andrea we described with CrazyChoir, which basically continues what we started in in QuireBot is a toolbox that allows really robots to do peer-to-peer communication, distributed, fully distributed, and truly distributed optimization control to be cooperative without any central unit. And then, as you can see there, when we started, then everything started to become nicer and nicer. And then we started with all the plugins and things that the guys will discuss. So I will really stop here. But before doing that, I just want to I asked Andrea and Lorenzo to put this slide here because really it's their job, it's their effort. Andrea Testa, first of all, Andrea Camisa, who started with the QuireBot, and then Lorenzo that put his effort in CrazyChoir, but also other guys that have been working on that. So with that, I'll leave the stage to Andrea and Lorenzo. So thanks, and I hope you will enjoy this description.
Thank you, Giuseppe.
Thank you. So thank you again, Giuseppe, for the nice introduction, and also thank you everybody for being here, and thank you also to other organizers that help us doing all this. So before going to the main topic of the talk, which is about CrazyChoir, I will just briefly mention so the toolboxes. The first one, as Giuseppe was saying, is QuireBot. So QuireBot was a ROS2 toolbox which was born with the idea of doing cooperative tasks. So, for example, distributed optimization or distributed control in ROS2. And at the time, we developed this kind of toolbox in which each node is in which each robot is indeed modeled by a set of independent nodes. And in particular, we have some kind of high-level nodes, which we call team guidance nodes, team guidance layer, in which we develop a set of routines to perform graph-based communication. So the user is able to provide a communication graph, possibly time-varying communication graph, and perform, for example, synchronous or asynchronous communication among different robots, which may be split, for example, on different workstations, or if the robot have the power to run a computer board, then they will just communicate leveraging ROS2. And then there are typical layers, typical nodes that are instead related to the low-level control part of the robot, so planning, control nodes, and eventually integration layer in case you want to do some kind of simulation. So we developed some routines to do numerical integration, for example, using NumPy and SciPy, as well as using other toolboxes like Gazebo or Weebots, as we will show you in CrazyChoir, or to interface with external toolboxes, so for example, Bicon. And the idea behind QuireBot was then to develop a full stack system for end-to-end fleet control, so both high-level cooperative among robots and low-level, and possibly to run experiment with heterogeneous robots. For example, we were able to run some nice experiments with both Tartobot and CrazyFly in the same arena, performing the same cooperative tasks. So, for example, pick up and deliver or surveillance. And so now the question is, how can we model distributed optimization algorithms and distributed optimization programs? So actually, this is an older toolbox. It's called Disrupt, and it was a toolbox that we developed on MPI in 2020. And here the idea is that Disrupt allows the user to model optimization problem. It was based on MPI, so it allows each processor to be an independent agent with its own capabilities to solve optimization problem locally and exchange communication using MPI in that case. With other processor using some user-defined topology again, but we developed Disrupt with the idea to be extensible also to other communication models. And so we integrated Disrupt in QuireBot in order to allow robots to indeed model optimization or cooperative task. And finally, we reached CrazyChoir, which extends QuireBot in the sense that it's still allowed to see the CrazyFly as a multi-stack object, which has a cooperative decision-making layer to cooperate with other CrazyFlies,
eventually on different workstations, to perform planning, to perform control at different levels. So as Lorenzo will show you later, we are able to both perform a really aggressive control, for example, of sending command rates to the CrazyFly, as well to send more high-level control. So for example, linear velocity input or position set points to the CrazyFly. And at this point, the user can choose to do simulation using, for example, Weebots or numerical integration. In Weebots, we included some Python bindings from the CrazyFly firmware in order to try to reduce the sim-to-real gap, or to perform experiments using the radio communication. I will give some more details on this later. And another nice property of feature of CrazyChoir is that indeed you can mix the two aspects, and you have, as we will show hopefully in the demo, some robots running on Weebots and some robots running in the real environment, in the real world. And we also include some basic GUI so that the user can, for example, hand-draw trajectories, can interpolate it to create some nice trajectory user-defined, and also to manage standard operations like, take off, landing, emergency stop, or start the experiment and the guidance. So please, Lorenzo.
Okay, thanks, Andrea. I'm Lorenzo from University of Bologna, and so how to install Quarbot? We start very well. CrazyChoir. So first of all, you need to check your prerequisites on Docker and NVIDIA in order to install the Weebots and use the simulation part. And then just clone the repository and we provide you some kind of scripts to just build the Docker image and then to create the container. And after do it, you can just start the container and execute it to execute our examples. What we want to show you today is an hands-on with an aggregative optimization framework. And in this framework in particular, we have a team of robots, CrazyFlies in this case, that wants to protect a target from intruders. In this application that we developed last year in ICRA, we have a team, we somehow model a basketball match team in which CrazyFlies has to protect the target, which is the basket, from the intruders, which are the attacker of the opposite team. And they want to place they want to protect the target from the intruders, but in the same way, they want to stay close together and steer the barycenter deformation to the inhibitor of the ball and the target. This is a global quantity, a global knowledge. This should be a global knowledge, but with our algorithms, we are able to track these global quantities with the trackers, with the tracker system, and the cost function of our minimization problem includes all the details that I said, which are the first part, which includes the fact that they want to protect the target from intruder, so place itself near the intruder. Then steer the barycenter through a target, which is the second element. And the third element, which is just to cooperatively stay together close to the barycenter. So the algorithm that we provide is just this is a brief sketch of the algorithm. So you should initialize the quantities, so the initial position of the CrazyFlies and the trackers, and then just update with the gradient flow the solution of the problem, and then update the trackers, which will track the two global quantities that we have, which are the barycenter deformation, which will track by S, and a part of the gradient, which is global, by the Y tracker. Okay, but how to implement a distributed algorithm in CrazyChoir? So we leverage Quarbot optimization-based classes, which are the optimization guidance, which correspond to the decision-making layer that Andrea showed you before. And then this class will run the optimization thread, which is external to the ROS2 thread, will run beside ROS2. And in that class, you should implement your own do optimize, which will run the optimization. And seamlessly, you should also implement your own actions, which are the optimize. And if you want to get back the results as we want for the local positions, you should implement it. And we also provide some master methods such as get cost to do some kind of post-processing analysis. Okay, in this example, so in the aggregated tracking, what you should do is just to include your aggregative CrazyChoir guidance, which inherits methods from the aggregative guidance, which is a Quadbot classes, which is which is part is the optimization guidance from Quadbot, and then just to specify your methods, which are the initial condition, where we will just send the position for the crazy flies, then the intruder if you want to have static or moving intruders, and then the target. And obviously, it depends on your controller, on your planner. You should specify also the generate reference messages. For instance, if you want to do some angular rate controller, you should tell them to send angular rates set points. Or instead, in this case, we provide an example with the velocity command controller. So we just need to send the position goals and then apply a tip to control it. And then we have the aggregative optimize, which contains the algorithm inside, and just to writing your problem and the cost function, which will be generated by the function generate cost. In this case, you can see where the algorithm is implemented, which is a script inside the aggregative utils folder. And as you see here, it's pretty simple to see the same structure of the algorithm I presented before. So the first part is where data have been, where the data are exchanged. So first retrieve the data from the neighbors and then send yours with the neighbor exchange, which is a mechanism implemented in Quadbot. Then update your trackers, S and Y, and the credit flow. After that, you just update the solution and restart again with the next iteration. Okay, but how to run a simulation in all this mess? So first of all, our main packages are Quadbot and CrazyChoir. So you will see this two folders, which contains all the methods you need to implement your algorithms. Then we provide you an example package, which is a CrazyChoir example, that if you are familiar with ROS2, will contain these at least these four folders, in which in CrazyChoir example, we gather all the nodes, the launch file, all the nodes that will be run by the launch files, which are contained in the launch folder. And then in the resorts and words, there are some Python script and a URDF file, and which contains the file that you need to run the simulation in Weebots. Okay, so this is the launch file that I will run later, where we just set the number of agents, then the communication graph with the agents, then the initial position and the target. Then you generate a word. Obviously, I cut some kind of line of code just to make it clear, and then execute for each robot the stack of layers. So for the guidance layer, we just divide for agents and intruders. So for the agents, we have the aggregative guidance, Instead, for the intruders, we just have a go-to class that will just send a go-to a position set point to the planner. Then we have also simple guidance just to perform the standard tasks such as takeoff, landing, and stop. And then controller, planner, and Weebots driver. In particular, here we just leverage the velocity controller that I told you before, and the spline position planner, which having a goal position, it will compute a spline and retrieve the set point for our controller. And then the Weebots driver, which contains all the things you need to link the Weebots object to ROS2. Okay. So Andrea, if you
Yeah, so while Lorenzo prepares, thank you, Lorenzo, by the way, the experiment, I will briefly recap what we did and show you a simulation. So here we are describing the main steps that you need to do in order to run CrazyChoir, sorry. And so here we are checking our NVIDIA in the case that we just want some smooth simulations. And here we created a set of scripts just to automatically build the Docker image and automatically create a container. So just to ease the creation of the virtual environment to the user. So you can see here, for example, user is indeed running one of our scripts to create the image. So for example, in that case was a demo image, and now he will run a script to create a container. So in this case, we call it container demo. And you will see now in a minute. So here is just the building of the package that you can see actually is quite fast. And we'll now show you the main classes. So the one that Lorenzo was introducing. So here is the launch file, the different nodes that are run. And the different classes that are bought from Choir, bought and from CrazyChoir. So if you have a really fast site, you will be able to see anything. But it was just set in case if someone wants to slow down. I suppose we put this video, by the way, on our webpage, so that one who is interested can indeed stop it and see where all the files are located. So just to give some more insight with respect to just the screenshot from the slides. And at this point, you can see that in order to run the simulation, you just have to run the launch file. And now everything, the magic will happen. So Webots will open. And you can see here that there is a target, which is the blue ball that the tree CrazyFly wants to protect. And whereas other three CrazyFly, which are the most outer one, are the intruders that will try to attack. So you can see that the inner CrazyFly start to move in order to go nearby the intruders. And as soon as the intruder move, the defender, which are running the aggregate optimization strategy that Lorenzo was explaining before, approach the intruder to do that. And at that point, the simulation ends with a safe land. So what we would like to do now is to try to replicate this nice simulation. So in order to do that, we need to change something. Okay, so what the main difference between a simulation and experiment is that indeed we have to communicate with the CrazyFly. So we created a set of handler, which we call radio handler, that help us to communicate properly with the CrazyFly, leveraging the Python libraries from Bitcraze. And in particular, we define some set of standard methods, which are the command sender, command stop, command takeoff, or set value if you want to change some value in the firmware. And we created different subclasses. For example, if you want to send set point position and eventually ground truth information from motion capture, angular rates, or linear velocity set points. And at this point, all you have to do is just to include in the launch file these radio nodes, and in which you can pass the radio address of each CrazyFly. And there it is mainly. So let's try to run the experiment.
Perfect. Good. All of them have a
Andrea, could you?
Yeah.
Okay. Yes.
I'm trying to stop it.
Actually, I looked at the best in case.
Yeah, it seems that it's worked. Perfect. So, as you see here, hopefully you're running the simulation, the experiment. And in this case, you will see 3 crazy flies, which are the intruder, which will be simulated by Weebots, and then 3 green spheres that will represent the actual crazy flies.
So here we are logging the data from the lighthouse system and show it in Gazebo just for
Exactly.
the
This is the node from the radio. So will tell us in a minute, I think, I hope, yeah, exactly, that the radio class is started. So we can perform the takeoff. And it seems it's working. And this is the commands that they run to the crazy flies. And then start the aggregate view example. And indeed, you see that the agents just placed itself in the middle of the intruder and the target. And they just react to the movement of the crazy flies, of the intruders. And in this way, you can perform even complex experiments in a mixed reality version. I can put this maybe in a top view. And for instance, you can even move the simulated crazy fly from the simulator and see that everything should be fine. I hope so. And if you move your crazy fly, the agent, the green ball, should adapt the movement to the other one. Okay. So even if you want to send the direct commands to the crazy flies, you can do it. For instance, now agent 3 is in position 101. And 101, we can put it in another position, maybe 0.6. 1 in 10 seconds, and just send it directly. Okay, you can see here it is moving. And it's trying to adapt the information, which is, I suppose, this one. Okay. And I think that it is, we are done. Okay. Okay, we should come back to that side. Just a minute.
So just a couple of works that we did in this context,
Okay.
and
They are seeing the visualization, but it's fine.
yeah, it's fine. Just a couple of works that we did in a sense. So those are the CrazyChoir and this ROT and Quarbot paper, as well as other papers in which we use this kind of technology. We recently submitted a tutorial paper on cooperative robotics and distributed optimizations on the precision of the IEEE, the second round. So hopefully it will go fine. And just a big thank you for your attention. And if there are any questions, we will be glad to answer.
Any question?
Yes, I'm not sure if there's anyone.
Andrea, Lorenzo, there's a question in the chat by.
Okay, just
how close is the simulation to real-world experiments?
Actually, it's really close, but in this kind of experiment, we do not model wind. So if there is no wind in the room, it actually perform very well. So let's
thank the speakers.
Just one quick question. If one robot fails, will the simulation suffer?
It depends on your algorithm. If your algorithm just in our case, never anything happens because by the way, if an intruder will fall down, in this simulation, the agent or the algorithm will follow its position, but not fall down because it's broken, but because it will follow the position of the intruder. Just for that. And because it is fully distributed, the control stack of each drone, of each robot is fully independent from the other. So if one fell down, the other one will stay together.
The network will stay up, like.
Yep. For instance, there is some kind of example with formation control that they all depends from the position of each other, and in the case, the formation will fall down, but because of they will follow the position, not because of the. Okay.
Is the behavior running onboard here or off-board?
Sorry?
The behavior, is it running onboard or?
No, actually, it's run offboard. Because the ROS2 until now we are not able to run ROS2 on the crazy flies. Or now we are just send the set points. Depends on which kind of controller you want to use. You actually use also the go-to controller from Bitcraze. So we just send the goal position, or we send velocity commands or angular rates.
I just want to add to that, there is micros available for the CrazyChoir. They have a demo that works on, I think there's an onboard that works on but it's all.
I mean, we were not able to do still, we don't have time to.
Yeah, CrazyChoir is not running on because we need some kind of Python libraries on it, so that's why Lorenzo was saying that we not able to run it there for sure.
It can run.
Yeah.
Sorry for being. Yeah, sorry.
And now we'll have a talk from the Learning System and Robotics Lab at the Technical University of Munich on behalf of Schoellig. His research focused on developing mathematical frameworks and algorithms for safe robot decision making, with particular emphasis on enable robots to operate efficiently in unstructured environments. So please join me in welcoming SiQi.
The other one is still being shared, the screen from the other talk.
Yeah, do you have to zoom in?
No, I think the other talk is still being streamed.
Yes, sorry.
Just there's a possibility.
Yeah, but
Good afternoon, my name is.
You can also disable your microphone because we have our running.
I think I'm disabling now. Okay, yeah, no should be good. So good afternoon, my name is SiQi, and thanks for having us here. So I'm from Professor Angela Schoellig's lab. Unfortunately, she cannot be here today, so I'm filling in for her and try to share some of the aerial swarm works from our lab. The title of my talk is Safe Decision Making for Aerial Swarms, from Reliable Localization to Efficient Coordination. So our background is really control for quad rotors, which are platforms that are able to carry out agile motions and very dynamic maneuvers. When we are working with such platforms, safety is very important, and incorrect input could mean that crashing the drone or leading to other irreversible consequences. So our research trajectory was motivated by this trend, where robots are deployed in increasingly unstructured and possibly dynamic environments. In such settings, robots are required to learn and adapt in order to complete tasks safely and efficiently. In the past, we have looked at how we can safely learn for single robots and then how to translate that to multiple agents.
In this talk, I will share some of the hardware and algorithm tools we use in our lab to facilitate the design of aerial swarm systems. And the talk is divided into 3 parts: robust range-based methods for reliable indoor localization, algorithms for safe and efficient swarm coordination, and lastly, simulation and benchmark tools for scaling up swarming tasks. And we'll start with the first part. So one sensing modality we have looked into in the lab is ultra-wideband radio technology, which are portable and accurate sensors that are readily available for robot platforms such as the CrazyFlies. And there are also potentially enabling technology for a wide range of robot applications, such as warehouse management, industrial inspection, and long-term monitoring tasks. One thread of our research is around how we can make the ultra-wideband-based localization algorithms more robust for indoor settings. UWB has 2 modes of operation. One is two-way ranging, where the UWB target communicates with the anchors and get the range measurement through two-way communication. And the other one is time difference of arrival, or TDOA, where the UWB tag receives the signals from the anchors and passively and compute the difference in distance as TDOA measurements. The 2 modes of operation have their respective advantages and disadvantages. In general, two-way ranging is more robust to geometry of the anchors and provides slightly better localization accuracy, while TDOA is potentially more scalable to large swarms. In our research, we explore both modes of operation and rely on the range estimates from the UWB for localizing the robots in indoor environments. While being lightweight and portable, one of the major challenges for UWB localization is that their measurements are often corrected by obstacle-induced non-line of sight and multipath propagation, which leads to biased and non-Gaussian air distributions. In recent years, researchers have utilized Gaussian mixer models to represent the measurement residuals. Using GMMs for modeling the measurement residuals alone would not be sufficient. In the context of localization, this is a 2-player problem. The computation of the range measurement residual depends on the knowledge of the current state of the robot, while the estimation of the robot state also depends on the model of the measurement residuals. In the past, this is often formulated as a bi-level optimization problem, where the inner loop finds updates the state estimates of the robot, and the outer loop refits the Gaussian mixture model to the residual measurement. This approach has shown promising results in the past. However, the current GMM-based model methods often rely on using the mean estimate of the robots, which ignores the uncertainties, and this can lead to suboptimal localization performances. We can observe this phenomenon through a simple example. The plots on the left show the ground truths and the estimated trajectories. And if we compute the range measurements residual based on the mean estimate shown in blue, then we would get the noisy residual distribution shown on the right-hand side. However, if we compute the ground truth state and use this for computing the measurement residual, we actually see that this distribution is in fact multimodal. And this multimodality would get lost if we do not systematically account for the uncertainties in the state estimates. To address this issue, two PhDs from our lab, Linda and Abby, propose an uncertainty-aware Gaussian mixed model method, and the core idea is to include the covariant matrix of the state estimates through a variational EM formulation. Based on the uncertainty-aware GMM algorithm, a bi-level optimization scheme is used to improve the localization accuracy. In the inner loop, we perform a posterior estimation of the robot state. And in the outer loop, we use both the estimated state and the covariance matrix to perform the uncertainty-aware GMM modeling. The proposed approach was validated in different indoor environments, and here we show one set of the results for localizing a quad rotor in cluttered cafeteria. The proposed method achieves an average of around 80 centimeter localization accuracy, leading to roughly 20% error reduction as compared to conventional GMM approaches. With a proper content of variances in the state estimate, we can generally achieve better positioning accuracy. And in a follow-up work, we then also show that we could further reduce the localization error by roughly 5 to 10 centimeters through fusing virtual inertial measurements with UW range measurements. And the plot on the left show a set of experiments in the same cafeteria environments, and the proposed VAO UW method was fully implemented on board of the quad rotor and is able to achieve similar performance as compared to the offline batch estimates that have full access to the full measurement history. So now we have seen that we could exploit UW as a low-cost sensing modality for indoor localization. One further issue for sensor fusion is spatial temporal calibration. And we from the lab also developed an online self-calibration method to account for non-collocated sensors with different temporal latencies. The online calibration method can generally further reduce the positioning error by another 10 to 40% as compared to hand-tuned methods. Now we have seen UW-based localization for single drones. The transition from single agent to multi-agent does not differ that much, as the measurement model can be directly used. In this case, each robot would act as both a tag and an anchor. And just to add that, as may be required in some other applications, with UW tags, we can also, with multiple UW tags, we could also directly estimate the initial pose and the trajectory of the robot systems. As a summary for the first part, we have shown that UW can be used for portable and reliable robot indoor localization, and uncertainty aware GMM model learning algorithm can be used to further improve the localization performance in cluttered scenes. And fusing visual inertial odometry and spatial temporal calibration could further reduce the localization errors, and those approaches can be directly scaled to multi-agent systems. The second part of the talk is around safe and efficient aerial swarm coordination. So I will start this part of talk with a video from Angola. Well, I guess this has audio, and this will have feedback. So the idea of this work is really having a swarm of drones to move in coordination with the music. So yeah, I guess we cannot really hear. Yeah.
Power.
Okay. So yeah, I guess feel free to check out the video offline then.
Maybe your laptop.
Yeah, I think there was some echo. There was some feedback if I turn this on.
Yeah.
Yeah. Yeah. I guess it's okay.
I guess we try and. Can somebody recognize the song? It's dancing.
We're singing it.
Yeah, exactly.
Okay, yeah. Guess we'll just skip this for now. So there's a trajectory of our from our lab that works on dancing to the music with aerial swarms, and the earlier works were mostly focused on primitive-based motion planning frameworks for dancing to the music, where the motion parameters are usually hand designed by experts. Motivated by more recent advances in language models, we attempted to extend this line of work by incorporating large-scale models to generate creative motions and enable more intuitive interactions for drone choreography. From this conference, we have seen different ways of incorporating language models or visual language models to the robot stack. And in this work, we share similar motivation, but at the same time, we try to preserve the safety guarantees offered by primitive-based and optimization-based swarm motion planning methods. So here on the plots on the left-hand side show what we could achieve with large language models. We could, for example, ask the model to generate waypoints for circular or linear formations. In general, the large language model provides a means for interpreting qualitative instructions and allowing specification of behaviors through intuitive instructions. It is, however, still difficult or not intuitive to, or not trivial to guarantee feasibility and the safety of the generated choreographies through language instructions. So in our work, we introduce a safety filter that encodes the prior knowledge via distributed trajectory optimization framework. Intuitively, the safety filter takes in the choreography generated by the large language model as input and generates smooth and collision-free trajectories that best matches the choreography generated by the language model. From our lab, we have proposed different distributed swarm trajectory optimization frameworks in the past, ranging from earlier offline distributed MPC to online distributed MPC and to more recent alternating minimization approach that leads to less conservative behaviors. In general safety, the safety filter we use our distributed optimizations for individual agents to account for actuation constraints, smoothness, and the motion of other agents. And this is an illustration showing the idea behind our safety filter framework in a head-on collision scenario. So the gray dashed lines are the road trajectories sent to the quad rotors, and the blue spotlight lines are the trajectories of the quad rotors after the safety filter is applied. The red circles are the collision envelopes accounting for the physical dimensions of the quad rotor. And as we see, as the drones navigate through the center, the safety filter would modify the trajectories such that the three drones will slightly rotate and avoiding colliding into each other. And after the collision is resolved, the drone would tend to converge back to the default trajectories as shown in the gray. Based on, so this is an overall back to the choreography application. This is the overall architecture we propose. So the large language model would take in the peak times or some the output from some music pre-processing module and some language instructions from the user. And the language model generates a set of waypoints for and that is sent to the optimization-based safety filter. And from the safety filter, we obtain a set of certified trajectories that is sent to the swarm. We can either visualize this swarm behavior in simulator and then reprompt to achieve desired behavior or directly deploy it to the real system. Yeah, so the language model accounts for tries to interpret language inputs and generate waypoints, and while the safety filter on the lower level will account for any feasibility constraints and other safety constraints. And this is one numerical result which show the impact of the safety filter. So the blue bar shows if we directly apply the waypoint sent from the language model, then we'll have different, the orange ones will be before filtering. So those have different collisions, especially with a larger number of drones. We observe a larger number of collisions between different drones if we directly apply the choreography from the large language model. And then after we include the safety filter, we can ensure 0 collisions. And this plot shows what we could do with the large language model. In this case, we ask the model to generate trajectories that allows the swarm to fly faster. So before and after prompting, we observe an increase in the average speed of the quad rotors. And again, I guess we don't hear the music. So, so this is a couple choreographies that was generated by this framework. So we have tried up to 9 drones so far, and there are different ways of prompting. For example, we asked it to generate more symmetric motions and fly higher and fly in circular motions, and those were showing different demos. Yeah, if you are around Munich at some point, you're welcome to join us, and we can show this live. So yeah, so this is the second part. We'll show that we can leverage our prior knowledge and then use optimization-based methods for safe multi-agent motion planning. And language model allows us to incorporate allows us to design an intuitive interface for interaction. And similarly, combining the two would allow non-expert users to program the robot directly. So the last bit of the talk, will just summarize a couple benchmarks and data sets we have developed in the past that could help aerial swarm designs. And the first one is the ultra-wideband data set. So one challenge with working with ultra-wideband is this non-line of sight problem. So this would cause multipath and non-Gaussian distributions of the range measurements. So in this work, when the collected a set of data that allows us to, or allow one to build a sensor model to model the non-Gaussian distributed sensor model that allows better localization. And this is one illustration of how such sensor models could be used. And this work, we could incorporate the model and then optimize for the sensor placement to reduce the variance in the raw range measurements. And on average, this could reduce an error of up to 76% in 3D settings. And this is another simulator that was done by a former postdoc in the lab, which is Jim Piebullet-Jones, and runs Piebullet in the backend for simulating the dynamics, and then it's meant to for multi-agent reinforcement learning algorithms. And here are some illustrations of the policies trained with this framework. And this can also work with standard PID controller that is available from the CrazySwarm package. It's fairly easy to install, and yeah, feel free to try out if you're interested. And we then also another thread of our work is safe control dream, which the goal was to provide a means for fairly comparing reinforcement learning algorithms as well as learning-based control and classic control methods. So in addition to the Piebullet simulator, we also provide symbolic models for the quadrotor platform that allows model-based approaches to be easily implemented and compared. And this overall software has the typical dream structure that allows reinforcement learning algorithms to be directly applied, and also symbolic models for computing the constraints or the Jacobian Hessians of the dynamics and the cost functions. We have incorporated and tested various control baselines, RL baselines, learning-based control, and robust RL methods. So yeah, this is a quick summary that this includes a quadrotor platform, which is modeled after CrazyFlies, and have simplified scenario for 1D and 2D motion, and at least 10 different controllers being tested already. And those two are relevant publications from the lab. We recently also used this for a safe robot learning competition, and also used the same setup for product courses at two universities, University of Toronto and TU Munich. We'll soon release the version that we'll use for the course, and if you're interested, you can contact us. So a quick summary of the third part. We have presented a util UWB-based dataset to facilitate reliable estimation algorithm designs in real-world cluttered environment, and Piebullet-Jones that provides more simulation data for learning more complex tasks, and safe control dream that bridges the gap between learning-based method and safe reinforcement learning, and finally, a competition setup that enables them to real transfer for fostering reproducibility and solution diversity in robotics challenges. I guess with this, I will conclude my talk, and I'm happy to take questions.
For the talk, there is a question.
For the talk with the combination with large language models, what is like your current flight stack? Like, how do you run the CrazyFlies?
So we currently use the CrazySwarm as it is, and use the full state command interface. So use the language model generating waypoint, and this is translated to position trajectories, position velocity trajectories, and this is sent to the for the full state command interface. Yeah, we're also trying, I guess, trying to incorporate like the attitude interface right now. We're trying to work with the medical controller, but
maybe another follow-up question. For this, did you have to fine train or retrain the large language model, or could you just use something like ChatGPT?
yeah, we use mostly the ChatGPT to reprompting. Yeah, I haven't really fine-tuned it yet.
But you have to do a lot of prompt engineering to figure out how to task it.
Yeah, we have to like reprompt multiple times sometimes because the output is not necessarily always repeatable. So sometimes we get better ones and sometimes not as good. So that's why we have the simulator to visualize and to do this kind of also closed loop in that sense. Yeah.
There is another question.
Yeah, quick question, not to SiQi, but to everybody else, since I work with SiQi. Does anybody else use ultra wideband? Okay, I'm like wondering how much it's used in the community.
But we actually don't do the, yeah, we did the anchors as well, but also just ultra wideband on the drones, without external infrastructure. Yeah.
And Onboard and Bitgrace, we had like a big indoor show with the positioning system. It was like, yeah, how big was it? Like 20 by 30, yeah, 20 by 30 by 8. Something
Big
like that.
hangar. So in the Skybrush system, we support that with, we have a fork of the CrazyFly firmware with a library that is taking care of the async communication. A little bit, I think, a little bit better than the standard one, and there you can use the either the lighthouse or the UVB.
And you did it like with anchors or on the drones? Like
you had anchors.
Yeah, we had anchors, like,
You
yeah, it was about 16 anchors, I think.
So it's much larger territory, but less accuracy, so yes.
Yeah.
You focus on things like search and rescue, and then you cannot have anchors. So, yeah.
More for like factory inspection.
But maybe coming back to the ultra wideband there as well. Did I understand it correctly that it's a data set but not a predictive model, or did you manage to fit some sort of function to really be able to predict it by put the anchors here and have, I don't know, a wooden obstacle there, what say kind of behavior would be?
So the data sets were modeling the variance of the range measurements, and when the signal is blocked by different types of obstacles or different geometries. And then with this information, with the model the sensor with the variance, and then optimize for the position to minimize for the given environment. Then we minimize the variance with position the anchors to minimize the variance.
And is that an optimization that's in gradient free?
I think when they use like a Bayesian optimization framework to optimize the center placement, I think it's like sampling multiple points in the free space. As I said, the variance overall, this metric will be minimized.
Okay, so you assume it's a Gaussian model.
In the earlier work, I believe it was assumed to be Gaussian, and then the later ones, I guess he used more Gaussian mixer model to better approximate the noise. Yeah.
Okay, so thank you, speaker again. Now we have the last talk of this workshop, going to be presented by Martin Saska from the Czech Technical University in Prague, where he is the founder and lead of the Multi-Robot System Lab. His leadership has led his team to success in multiple and important robotic challenges during this year, such as the DARPA challenge. So, and I have to. It's a pleasure to have him screen here for his presentation.
Yeah. Your presentation.
I don't know where it was.
It would be just the two unless you want to lower it. No, just the two is what you see, and then you just move the window. This will happen. Okay. Ah, no.
Okay. So maybe let's go.
Is it Andrea? Is it okay?
Okay, perfect. So thank you. So thank you for the introduction and thank you for inviting me for this workshop. In fact, I'm going to back to the real world environment, and I'm also going to start with the same motivation as Gábor did. I don't know why the video is not running. I hope. Let's see. So I will be talking. Let's see. Yeah. So my motivation is also swarming in real world conditions. It's completely frozen.
Yeah. Is everything?
It's like frozen.
Okay, but it's
So-
everything frozen.
Exactly.
We should restart again the presentation. Come on, you.
That will happen.
Oh. It's everything frozen.
Exactly.
You should run it on a CrazyChoir.
Makes it the most look easy.
They've been doing pretty good so far.
Yeah, I must say that that was good.
Really impressive.
We shut down everything. Maybe.
Yeah, but how? It's nothing. It never happened.
Not press the power button.
Even this is not working.
Is there maybe another, I guess we can.
Have you tried from here, maybe? Or just enter the password and we try what Andrea is saying.
What is the data? Okay, so this is.
Which is maybe this one?
So maybe just
Or
here.
dance.
Okay, now I maybe know. No.
I guess,
Okay, so perfect. So
It was because of Microsoft PowerPoint.
yeah, exactly. It's Microsoft PowerPoint.
Microsoft's fault again.
Yeah,
Exactly.
Yeah, so that,
So I'm not sure if I have to go to the Zoom or if I'm not able.
Lorenzo will receive some other.
The first one from I'd love to be in charge.
yeah, but those are the ones. No, not necessarily, I'm just.
Are you still on?
Okay.
Now it should
Try to teach now. It's horrible.
So Andrea,
Yeah, but it's not okay.
it's not shared.
No, I also left out.
Yeah, it's a lot of services.
We try to close all the other.
Yeah, but we are not able to see it on Teams. We don't see the screen shared.
Could you-
So maybe you have to share the screen again.
Yes.
But then you know what will happen.
Yeah, if it's really not possible, maybe I can, yeah,
Oh, you
like
can.
maybe make a video.
Or the video and
Well,
share
the
it.
hour
Yeah.
is also partially recorded, right? I'm not sure.
Yeah, but
Okay, let me try it last time. It's not working.
The other few minutes.
Okay, now I can see it.
Now you can see it, but it's not working.
Okay, so it's apparently taking up too many resources.
I think so.
Yes, I'm announcing without Zoom, and we just hope that, like, just record basically the hour part.
Yeah, but if Kimberly wants to.
Yeah, but so you can already give like, maybe just unshare your screen. I will try to set up some kind of extra video and then you guys can.
Just go without
Yeah.
screen sharing.
Yeah, exactly.
Without screen sharing.
Yeah, there will be probably partial recording, but in the meantime, while you talk, I'll just try to get a recording of the screen itself, but. It is what it is.
Yeah, maybe you will have to reboot PowerPoint again.
Okay. Anyway, so
Even better.
Yeah, so we lost 7 minutes, perfect. And yeah, my computer is really not cooperating.
You can try to send my presentation.
And or what about trying to do it like
Was the same on my laptop. I use HDMI.
what really? Okay. You could tell us.
Yeah.
Let's see, I have there's one video on now with the screen. That's me.
I can just put it a little bit more. Because
Okay, yeah.
I'll follow
Like this?
Okay, perfect.
Yeah?
Perfect, yeah.
Okay, this is the best we can do at the moment.
Thank you for solving the issue. Okay. So let me start. So this is my group. Now we have 45 employees in the group and many master students and bachelor students. All we are working on aerial robotics and multi-robot systems. Our goal is to deploy flying robots in real-world conditions. That's why I will present you some tools, offer you some tools for swarming. And also I will try to show you some success missions we did with transfer of multi-robot systems into real-world applications and into industry. So we are really even selling multi-robot systems already. So you will see how to get from fundamental research papers, let's say, into applications and then into industry. To be able to do that, let me introduce also our spin-out company. It's called spin-out because it's not owned by a university, but it's owned by people working at the university. So we have established the company with two my colleagues, and the company is growing a lot. Now they have 35 people. I'm not involved anymore too much in the company, so that's why I say they have. And they are still hiring. The last year they managed to get like income for selling multi-robot systems already 2 million euro. So you can see that it's kind of already working business. And this year they have achieved already now 2 million. So probably we will again like 2 times multiply the income for selling the multi-robot systems, I would say. But why didn't should be moving? Oh, anyway, but back to the research part. This slide is now already 12 years old. At that time, we were starting with the idea of building a real swarming system for the real condition. I was also inspired by the videos that Gábor has shown us, the flocking of birds and schooling of fish. But that time already there were some results, mainly from his group, but we were like, okay, but they are using GPS, they are communicating. In nature, animals are just observing the others in the proximity, and they are able to be stabilized, they are able to fly in a flock or swim in a school. So let's try to do that. I tried to apply for funding, but it was rejected because the application was weird. We wanted to fly outdoor, high altitude, but without GPS and without communication. So the answer was like, why to do that? GPS is everywhere. Communication is so easy to get. So we decided to go more to environment with obstacles. This is why our motivation was also to deploy the system to high density of obstacles environment. And of course, we wanted to be decentralized, without communication, without GPS, and be scalable and to achieve really large teams of drones. Now the motivation of flying without GPS and without communication, even in high altitude, is here. But unfortunately, I would say, you know what I mean. Anyway, so as I have mentioned, the main instrument, the main tool for such a swarming without communication and without GPS is relative localization. The birds, the insect, fish, they all can observe the other teammates in the proximity, and we have to design a sensor to do that. And such a sensor should work in real-world conditions, out of the lab. We have designed many different algorithms. Of course, we published all of them, so I could promote all of them because we have them in good journals, but don't use any of these, I would say. So we have tried RGB cameras with CNN networks. Still, we are working on it a little bit, but you know, it's so difficult to detect the drone, which is like in front of trees, and here is a drone. Come on, even the CNN cannot find it, and plus we can't use like huge computational power. We need to use small computers on board and to have output. Before 30 hertz, now we are flying much faster. So even like now we are talking about 100 or hundreds of hertz. No way with CNN. Stereo cameras. Doable somehow. This blob is a drone, you know, but here you have a lot of similar blobs, and how to find that this is really a drone. Again, you have better resolution. Again, you need high frame rate. Then we have tried 3D LiDARs. I will show you maybe a little bit later. Again, in some situation, it's quite promising. If you are close to each other, if there are no more obstacles, it's working. But in real world conditions, very difficult. 3D LiDARs are still bulky and expensive. We have tried RGB lights. this was better, but still you have a lot of light in nature and it's difficult to set up the cameras and everything. April tags work quite well, but only in good visibility conditions. We have tried also UVB. If you have beacons, it works very well. If you put them on board, it works. You can on the given conditions work with such a system, but if you go to real world conditions, you have obstacles. It's not reliable at all. We wanted to have something which is like really reliable tool on which we can build something. So based on these 12 years, I would say, or it was already during that journey, one of my students came with an idea to use UV part of the spectrum of solar radiation because this part of the spectrum is filtered out by the atmosphere. So in fact, if you place a filter which allows to go on the chip of the camera only the UV part of the spectrum, you have a black image, except the situation where you directly point to the sun. Of course, you may have some reflections of the direct sun, but in most of the cases, it's a black image and we have only small dots there that are our active UV LEDs mounted on the neighboring drones. So this technique is the most reliable for various conditions. We have done a lot of experiments indoors, outdoors. We have even installed this system on some products of the company, and it is working very well. As I have mentioned, we can have problem with reflections, which could be like a false positive. That's why we have implemented a mechanism of blinking of these LEDs and a special detector to detect the frequency of the blinking. By that, we can distinguish between the reflection from the sun or from some artificial sources of UV in case they are in the nature, but mainly we can even communicate. And as we are now having higher and higher frame rate, the communication is better and better. And now we are working even with event-based cameras where we can achieve already optical communication, which again, back to that dual purpose applications, which is very difficult to how to say it, like jam, exactly. Thank you. We have, as I've mentioned, we have already successfully provided many, I would say 20 plus drones for the research universities with the UV radar on board. But I would like to spread it into the community much more. That's why we have designed such a drone, which is provided with onboard computer, with UV radar, as well as with UVB technology. UV radar can estimate quite well the bearing. The distance estimation can be also provided because we know how far the LEDs are, but that information is not precise. But UVB is very precise. So it can be used only even with two beacons, kind of one on this drone, one on this drone, just measuring the time of flight between the two units. It's quite precise, or I would say much more precise than any other technique. Yeah, it's funny that Wolfgang has started with a motivation picture, and I found the drone very similar as this one. So this was a result of AI, right? So this is a result of human brains, and probably they got the same kind of input. I also asked them, please make a drone for us, for the swarming community, which is able to do AI on board, which is able to work in real conditions. So this is intended to fly really outdoor. It is a strong system. It can fly in a strong wind up to 70 kilometers per hour. So it's like a really already like something, I would say. So in case you would be interested, now they are taking pre-orders and the interest is quite high. Another tool I want to introduce to some of you know it maybe, is the MRS UAV system for deploying swarms of drones outdoor. If you compare this system with Gábor's system, the difference is that this is more for research. It's also completely open, but it's based on ROS. It's modular. It's huge, so you can find there many different controllers. It goes from the lowest level control, PID control, SE3 control. There are different now nonlinear NPCs there, but it also includes many different sensors. So you can easily use 3D LiDAR, vision-based SLAM, 3D LiDAR-based SLAM, many motion planning techniques integrated. It's really bulky. You can find there everything you need for deploying of multi-robot systems in real-world conditions. Now we have more than 1,000 active users. The total number is much higher because we are using this system for our summer school, and we have already trained more than 1,000 students. So there could be there, but I didn't count these. So these are the really active users. And many of the summer school students are the active users. So after designing these two, let's say, enabling technologies, these two tools, we were able to fly in the forest as I wanted. But you'll tell me, come on, Martin, this is not swarm, it's 4 drones. And you are right. Come on, they are flying really slow. The birds are flying much faster. You are right. And of course, this is an experiment after 1 day of training, tuning, and cherry picking. You know it. So we found that, of course, flying high altitude, and this was already at the time where the other motivation was happening. So the client was interested in high altitude flying, far from obstacles. We managed to do it. So this is fully decentralized, without communication, without GPS, only using the onboard UV-DAR plus all the other sensors for obstacle detection. At the end, we managed to, now our record so far is 25 drones being stabilized only by onboard sensors. It's already a small swarm, maybe, but still not enough for me. So I specified few fields we are now focused on to really achieve the video Gábor has presented. This large swarm of birds that are like fully decentralized, without communication, without GPS, and flying fast. So the first one is agility. We want to design now fast swarming, the same technique as you could see in the Davide Scaramuza's demo on the conference. Nonlinear control, but also fast perception. We are going to the real conditions. We are not flying in the arena as Davide did. So the challenges are a bit different. We want to design a reliable system. While flying above the desert, far from obstacles, we manage many problems with perception. If you want to rely on vision, for example, here, and you don't have many features in the environment, it's kind of degraded environment. And this is the same with 3D LiDAR. This is from DARPA Subterranean Challenge, where we've had some problems with 3D LiDAR in long corridors. You can imagine that problem with degraded environment. So how to deal with that? How to include it, or maybe use advantage of swarms. I will show you. Then now more and more clients, and the research is going this direction, require long-range missions, which means if you are not using GPS and you are mapping, you are doing SLAM, you have to store the huge map, even share the huge maps, because we are multi-robot system. So this is also challenging. How to deal with long-range missions. The scalability, I want to go to thousands. And also, we have many applications and many clients requiring heterogeneous systems with different dynamics. So at that point, that small point, it's already less classical swarming where you have all the robots the same. Yeah, so let me now present you briefly achievements we did this year, in fact. So all these conferences will be IROS or ICRA or journals this year. So we have designed non-linear planner, it's a model predictive part integral control planner for agile UAVs flying in an environment with unknown obstacles. So it's a bit different from Davide's approach. Here it's completely unknown environment, it's outdoor, and we had to challenge the problems with like fast update requirement. So we need 100 Hertz replanning to be able to fly the same speed as Davide. But outdoor, in real world, unpredictable outdoor conditions. So we manage that. We are flying now outdoor. It's super fast. I hope the video will be running. Yes. So this drone is using that planner. It's avoiding virtual obstacles so far. So we haven't, this is ongoing work to do also perception for such a fast flying drone. In this experiment, you could see we were flying 3.5G, 140 kilometers per hour. Our record is going to 5G now, and it is more than the F-35 fighters. So it's already quite impressive. So there is some ongoing work on the perception. For example, this is, let's say, super fast onboard robotic localization using event-based camera. So this is a short record of just a few seconds of two drones that were flying relatively to each other. And you can see even that we can even see the props as they are turning. So this is ongoing work because we need such a sensor, which is probably also, or it is bio-inspired motivated. So probably birds are using a similar technique where they are interested mainly in the events because everything is super fast, right? And they have a lot of colleagues around. But let's move into the second motivation, let's say, which is the increasing of the reliability. We were thinking, okay, you are all swarming guys, and you know that it's much simpler and more reliable to deploy one drone than 100 drones. Bringing swarms is always bringing complication and decreasing reliability. Although in the swarming literature, you can find that motivation of using swarm is higher reliability, right? So we are thinking, okay, let's try really to use swarming to increase the reliability. And the motivation was, as I have mentioned, the environment with not enough visual features. We were flying in the desert, and in some parts, they were really flat sand without any features. But like 20 meters next to that, there was a bush, or some, I don't know, camel shit or something, it was really that. And this could be used as a feature, but only for the particular drone. The neighbor couldn't use it because it couldn't see from its perspective. And this drone, as you know, if you don't have GPS and if you don't have visual feedback and you are just relying on a bad IMU we have on the small drones, your drone will crash in 2-3 seconds, which happened to us many times. So we try to use the UVDAR as a linkage, which is connecting the drones together and helping the drones which are flying above environment without visual features. In simulations, it worked, but in simulation works everywhere, everything, as you know. So I didn't trust the student that it's possible, but he convinced me. This is a very similar situation. You have also a problem with cameras above the grass. So we are using down-looking camera, but to be sure, I asked the student to switch off VIO on 5 out of 6. So only one drone is equipped with functional VIO. All the others are flying blindly, so they would crash immediately. So they are using the correct one as an anchor. So this anchor is connecting the swarm to the kind of global frame, right? Measuring the relative velocity to the ground, and it's working. So in reality, of course, you would expect that sometimes some of the drones will lose the VIO, so it will be even more reliable. This is also like cherry picking, you know, it was one experiment out of maybe 10 or 15 trials. But if we tried just to remove one VIO from one drone, it worked perfectly. Yeah, but that student is really good, and he told me, okay, I would like to try a situation where none of the drones will be equipped with VIO. All of them will be blind. And you know, as I said, 3 seconds maximum. So in this situation, only this drone is not connected to the others. These 3 are connected by UVDAR. They don't have GPS, they don't have VIO, any other localization system relatively to the ground. They can't measure their flight speed, which is needed in the control loop. So I will try to run the video. I don't know why it's stuck again. Now it's running. Oh, I will lose the wow effect. Okay, so now this drone crashed. Can you see 3 seconds? And the others are moving. It was not intended. They didn't want to move, but there is a drift. Of course, you know, IMU is drifting immediately, but since they are like, keeping hands, they are like relatively stabilized. And in simulation now, we can show that if you are going to like tens of completely blind drones, they will stay hovering because, you know, the error of IMU is random noise. And if you sum of these random noises, you will get almost 0. For me, it was a very surprising foundation. Another stream going towards the scalability to have hundreds. There are some studies in biological literature that the birds are observing the density of the swarm around rather than all the small individuals. It is well known that starlings, they observe only like 5, 6 neighbors around, and then the rest is shadow, right? Something. They probably observe the density. So we tried that. We design a system using neural network, this time from RGB camera images to detect the density of the swarm around. And we use this information for swarming. And it works pretty well even for swarms of thousands, where it is extremely difficult to identify positions of individual teammates around because you have overlapping, you have, you know, many drones close to each other. So CNN was confused, mainly the one which is possible to use on board of the drone. So you can, it was presented in ICRA. And we are now working on like real world experiments. Now, let me go a little bit. I have to be fast due to my bad computer. Let me go a little bit to the heterogeneous systems. We have done some interesting work of multi-robot systems of or swarms of drones, where some of them are equipped with 3D LiDAR. Some of them are blind. And that drone can control kind of the small drone by a 3D LiDAR detection. This works very well indoor, but even in such a condition of the forest, we tested it. So this is one of the few examples where we used 3D LiDAR. I don't have time to go to details, so if you are going to IROS, you can visit the presentation. Yeah, these are some videos how this drone is guided by this one. So it's really sending the commands to this drone. So here we are using communication. Another example of a heterogeneous system is cooperation of drones and USVs. We have done some designed some experiments for landing on a moving boat. We have designed also a system which will be also presented at IROS for cooperative manipulation of a floating object by autonomous drone and drone, all controlled by nonlinear NPC. This is on also IROS presentation on multi robot coverage planning for huge areas. So here we try to go to really long range missions. This is one of the examples, also IROS, where we managed to get from like the multi-robot systems into industry. So here we, with a company which is designing small quantum cameras for detection of radiation sources, we have designed a system using a swarm of robots to precise detection of source of radiation. Yeah, so I don't have time to run the video. So there will be like 3 drones scanning an environment and localizing multiple sources of radiation in the application of lost source of radiation. The system has been already sold many times, so it's already like available and working. Our company is providing the platforms. Another success story in the transfer to the application was the research of inspection of infrastructure for high voltage like electricity transmissions, so the towers. We have designed many algorithms for multi-robot scanning, even with cooperation with human. I will skip these because I have to finish. Anyway, we have designed many of these algorithms, and we didn't expect that the companies will really like it, but this happened. So now we are already selling these multi-robot systems into Germany. The company E.ON, which is kind of in charge of inspection of the high voltage infrastructure in Germany, required multi-robot system. They are now using single robots, and they are not sufficient because, of course, Germany is a big country and they have a lot of power lines. So it's great. And very last slides. This is an opportunity for you. If you want to cooperate with us, we got a European project which is like mainly to support cooperation. Within that project, we have established open remote lab. This means that you can send me applications, and in case, it is doable by our platforms, European Unity's project will pay all the hardware designers, all the engineers that are needed to support your experiment. So you will get the experiment for free, and you don't have to pay anything. The only what you have to pay is to cooperate with us and with the company, and they will provide you the platforms, and you will do the experiment remotely or in Prague. And of course, summer school is coming soon, less than 2 weeks. Still, I found that we have reached the capacity this year, so we will have 240 students on site. but some of the students didn't get visa. So in case you would like to come or your colleagues, let me know. We have 5 slots now. That's it. Thank you for your time.
I'm sure that we have time for a few questions considering the technical difficulties. So anybody have any questions for Martin at this moment?
When is your flight stack moving to Rust or to not using Rust at all?
Oh, good question. Good question. For me, like, since I'm sitting a little bit on 2 chairs, so at the university, I can't convince the guys that are working on this MRS system to go to ROS 2. Maybe Tomáš Báča, he's the main author of it, and he's still convinced that the ROS 2 is not ready to be able, there is a lot of bugs to really rewrite everything. But Fly for Future, they are working with ROS 2, mainly because their system is much smaller, I would say. So they don't use everything. So yes, and to say true, they struggle a lot. So they have quite a huge project together with maybe TII in Abu Dhabi. It's usually main sponsor of IROS ICRA now, and they are designing the ROS 2 system with them, and still a little bit nightmare, but being better and better. And without the ROS, yes, we have some, or they have in Fly for Future some industrial applications that are, for example, now they are working also on multi-robot. I feel it will be multi-robot inspection or surveillance of a perimeter to protect nuclear power plants, and this must be really reliable. So, and it is pretty simple. So it's without trust. Yeah.
Anybody else?
Regarding how you manage to fly outdoor all this time, you have very backup pilots for the drones, or
no? Good, but very good question. We don't have any. The last experiment with the same number of pilots and drones was with 4. After 4, my guys decided that there is a kind of possibility to switch off the experiment. So we have just a red button, to say true, because you can't. Maybe it's not problem that we don't have the people. Maybe we could find 25 pilots, but then you can't see which drone is yours. And this is already if you are more than 4. And it happened that there was a drone in trouble, and the wrong safety pilot tried to save the drone, and 2 drones were broken at the end. So they call it like cascade safety routine. So in fact, some button, if you press it once, everything is stopped. If you press it twice, they are landing on the position where they are. If you press it 3 times, they will switch off drops in the flight.
And can you get through the European regulation with all the commercial products of this non-pilot autonomy stuff? Because it's very hard.
It is, but I have to say that Czech Aviation Authority is very progressive and proactive. We have really good relationship with them, and yeah, sometimes I don't care, but if they don't say no, but yes, so far there was no problem. So they can understand. In fact, they have the same requirement as if it's with piloted, or I mean, so they allow even now BVLOS flights. Of course, there must be some kind of safety pilot, but this is the same. In fact, for me, I mean, it's also there is a stop button. So they already can accept that. At the beginning, they had problems with swarming or with many drones. They kind of found a rule, especially for us. Nobody else is using multiple drones. Yeah, it was doable. So no problem. But I know that people from Germany are going to our testing field, for example, which is good. I don't care.
Okay, I think that will be the last question, also for you, because you also need to. So let's try to wrap a couple. First, of course, give a hand to the speaker. Let's try to wrap things up. Thanks a lot for joining this workshop. This was like, you know, it happened like almost a half a year ago that we contacted like, you know, the organizers to kind of connect us together, because aerial robotics is a difficult field. Swarming is a difficult field. If you combine that together, it's super hard. I can definitely remember it from my PhD, that with the first platforms that was in-house and, you know, prototype, I was like, yeah, I didn't trust them at all. You really need to trust your platform and the communication platform to really get swarming to work. Also a lot of thanks that at least organized for the tutorials were able to willing to show the demos on the CrazyFly as well. So in that sense, that's thanks for showing off the capabilities, of course. But I think also what I find more important is that we were able to find look at different fields of aerial robotics as well, and able to learn from each other, from also like the outdoor, the indoor, the stacks that do both. I saw quite a lot of similar topics or similar modules that we use in either ROS2 or the own software packages that we make ourselves. And I think this workshop was very much to learn from each other, to kind of see what the overview is of what's currently possible. And luckily we didn't only sell CrazyFlies, even though I work for the company who make the CrazyFly. So of course, like, we're happy, but it's also very good to, as researchers for swarming robotics, that you have the platform that works for you. So yeah, CrazyFly is nice, but it cannot carry too much. But yeah. Thanks again to Gábor, Martin, SiQi, and of course Sabine, if she's still there. A lot of thanks to my co-organizers, Miguel, Rafael, Andrea, Lorenzo, Wolfgang, of course, and Giuseppe, if you are still there. Thanks a lot. And some technicalities, there is a reception still in the aula. I don't know until when, but you can still come together while we pack up here, because we do have to pack up. And also for those that have to catch a flight tonight, please check your flight, because there was a lot of trouble with Schiphol and Amsterdam Airport today. So do make sure that your flight is not delayed or something like that. Seems that they've covered some, but just as a warning if you happen to catch your flight tonight. Thanks a lot again for joining, and hopefully in the future we'll have another one.
Yeah.